about artificial intelligence for photonics. We have a very interesting lineup of speakers this afternoon. And for the very first speaker, we're glad to have with us Professor Yoni Dambre, who's a professor here at Ghent University. And she's very active in research related to different aspects of machine learning, unconventional computing, and robotics. Now, we all know that machine learning can seem a bit like magic sometimes, but in her talk, she will try to dispel that magic and give us an introduction to the different aspects of machine learning. So, Yoni, the floor is yours.
Okay, thank you, Peter. Welcome, everyone. I saw there are a huge number of participants. So yes, I was asked to give a brief introduction to machine learning, and I have taken that up from the perspective of, say, beginners, so people who are not experienced at this moment with machine learning, although I'm sure that probably other people will also still be able to learn something. Now, the time is very limited. The field is very broad and very deep, so don't expect any advanced stuff. I will really focus on the fundamental concepts and principles, and also, very importantly, a number of commonly occurring pitfalls. Okay, so of course we'll start with identifying the field. So what is machine learning? And I'll identify this based on the components of machine learning. So in machine learning, what do you need? You need data, you need a parametric mathematical model, you need a cost function or loss function, so you need some kind of way to evaluate how good your model is, and then the right-hand side, that is where the magic occurs, so that is the learning algorithm, the optimization, the training, if you want, of the model. So if we combine all these elements, what does machine learning do? It's optimize, and we commonly call that learn, but basically some kind of optimization problem. So optimize the model parameters to minimize the loss function and using the example. So that is what's happening in machine learning in contrast to, say, traditional algorithmic approaches. So in traditional approaches, you split up the problem in a lot of different steps, and then you code these steps into a computer algorithm, and the algorithm does it for you. That requires that you know the steps, that you know how to achieve the answer. So machine learning is typically used in those situations where just using your brain and trying to identify the steps just doesn't work well. So that's where learning comes in. Okay, so just a very brief overview. So there are a number of big categories of machine learning. So the first, and I think at the moment still most common category, is called supervised learning, where your model basically approximates a functional relationship between the inputs, so the features from the data that you measured, and some kind of design.
Sorry, Yoni, to disturb you, but there is quite some noise from your end. I don't know if you can talk in closer to the mic or something.
I don't really have any way to change my audio. This is the way I commonly record lectures in class. So
the voice quality is indeed not superb.
And I'm using a microphone, so it can't be through the.
Yeah, it's not superb.
There's not really much I can do here. Does it change if I move the microphone?
It seems better now.
You're sure you're using the device you think you're using? Perhaps, I mean, sometimes Teams changes the microphone settings behind my back. You might be recording from your laptop
maybe.
Instead of.
Okay, I'll see if I can. Does anyone know where to access these things? Maybe it's not using my microphone. That's possible.
If you go to the 3-button menu, they have device settings. Perhaps you're picking up the wrong microphone.
Do I see that?
Yes, the
show device settings, the top one.
Here.
That doesn't sound good.
Now further down, yes, here, built-in microphone.
This one.
And change the speaker as well.
we can't hear you now. I think you need to select a different one. Different microphone.
So somebody is still unmuted. So perhaps if you could all mute your microphone. Thank you.
Okay, can you hear me?
Crystal clear. Perfect.
Much better.
Okay, I had to close the whole thing and start all over now, see if I can find my presentation again. Okay, and okay, this is sort of where we were.
Yeah, you're all set. It looks good now.
Okay, great. I'll just see if I can close that thing. Okay, so we were at the different types of machine learning. So the first type is supervised learning. So basically you have data and you have examples of what your model should give as an output. The second type of machine learning is unsupervised learning. So there you do not have labels, you do not have desired outputs. You want your model to learn like what is normal in the data. So the structure in the data, the dependencies in the data. In more mathematical terms, what you usually learn is a probability density profile of the data. And then a third category is reinforcement learning. So there you have some kind of supervision, and we call that a reward. But that reward does not have like a mathematical relation to what your model actually gives as an output. So you have some measure of how good it is, but since the optimization techniques that we use really need this mathematical relation, so you can't use traditional techniques. So that's a whole different family of models. Okay, now I really need to see if I can. Now my pointer doesn't work anymore. Okay, so supervised machine learning, as that is what we know best, is then again divided into types. And one type is regression, where the labels, so what your model needs to output is just real values, continuous labels. And this is just an example. So in this example, you have measured two things, two numerical values, a temperature and a time. And then the third thing is the power is what your model needs to predict. It's no use here to go into the details of this particular task. But so these predictions need to be continuous value. And the surface that you see there could be what the model tries to do with that data. So it tries to approximate where these data points lie in this 3D space. Now in classification, then you have a number of discrete classes. Usually these are mutually exclusive. So for each data sample, you need to say which of the classes, in this case 3 possible classes, your data belongs to. So what happens there is, again, underlying, you have a model that predicts some kind of surface. In this case, the surfaces are just linear hyperplanes. So you see 3 surfaces in the figure on the left. And then for each new data point, you find which surface predicts the highest value. Often these values are even interpreted as a probability, not here, but in other cases it is. So you take the surface that predicts the highest value, and that is the class that you predict. So if you translate that to the picture on the right, what happened there is you took all the places where multiple of these surfaces are intersecting, and these become the separation lines between the classes. So we've had regression, we've had classification, typical examples of supervised learning problems. Now in unsupervised learning, there are also many different families, but just to give you one example, I'm going to take the example of a Gaussian mixture. So now you have the data. In this case, the data is just one number, one feature. And then you start from a number of assumptions. So in this case, in the Gaussian mixture model, your assumption says that your data consists of a certain number of clusters, subgroups, K, and that each of these subgroups has a certain probability of being sampled. If you would just randomly select data from the world, each subgroup has a different kind of occurrence. And within a subgroup, the features, so in this case, this one variable, follow a joint Gaussian distribution. And then what the model does is to tweak all the parameters, so the probabilities of each of the classes, plus the parameters of the 3 Gaussian distributions in this case, so the means and the standard deviations, to optimally fit the data you observed. Now, this is a very simple example from a larger class of models that is called generative models. And what is the nice thing of a generative model? That it is actually a probability density function. So you can sample from that and create new realistic data. Of course, realistic if your model is good enough, because if you think your data contains 3 subgroups, but it's actually 4 or 5, for example, then your model will not be good. Okay, so there are many different ways of trying to categorize the whole big world of machine learning. This is one of the examples that I found online. The bottom line there is that none of these categorizations is actually totally accurate, but this is one of the ways that it's typically being done. So there's a whole zoo of types of models out there. Most things have been invented multiple times. There's lots of literature, and it's really hard to find your way in that if you really want to dive deeply. Okay, so a last thing I wanted to say in this part. So there's the whole confusion, and in the media you usually read about AI. This talk actually also has a title related to AI. But actually there's these 3 different things that are often being mixed up. So actually the field is artificial intelligence. So artificial intelligence is trying to make machines do things that we usually consider as intelligent. Machine learning is doing that by this learning trick that I've just been talking about. So not by devising an algorithm, but actually by learning to mimic the example data that you get. And then the most recent trend is deep learning, where specifically one type of model is being used, actually a whole family of models, and these are deep neural networks. So most of what you will read in the papers now about AI is actually deep learning. So what I'm talking about is machine learning. And then there's also a whole bunch of AI outside of machine learning. Now that is commonly called traditional AI. And all the machine learning that is not deep learning is called traditional machine learning. So this field is rapidly evolving. Okay, why has this been having a big breakthrough? Because in the previous slide, you see the timeline at the bottom. So the deep learning thing is really recent. By the way, this timeline also does not show that AI has actually had a few winters, cooling down periods, and basically these were driven by the fact that people had huge expectations, which at some point could not be fulfilled anymore. So at the moment, some people are also thinking that we are again going to bump into one of these walls. But anyway, so why has AI or machine learning or deep learning been booming so much recently? Well, because to do complex things, you need complex models, and to use complex models, you use a lot of data. And the things to facilitate that have only become available over, well, say the last decade or so. So now we have big data, we have big GPU farms, and now we really can train huge, big, complex models. Okay, so what do you need if you want to start into machine learning? Well, machine learning combines a lot of different fields. So we have mathematics, probability theory, statistics. That's what you need to understand the models themselves and their properties, basically. On the right-hand side, you see the computer science skills. So you need to be able to program. You need to know about optimization techniques. You need to be able to do data manipulation, visualization. And at the bottom, you also need a domain knowledge. You need to understand the problem that you're trying to solve. You need to understand the data. You also need a critical mindset, a lot of common sense, and a lot of creativity. And so in the beginning of the latest boom of machine learning and deep learning, so the top levels were really much more important. But at the moment, most of the mainstream techniques have found their way into tools, libraries that are relatively easy to use. So now actually that bottom part is, well, at least in my view, for the users of machine learning, becoming the more important one. So that's sort of what I'll be focusing on most in this presentation. Okay, so I've talked about the components of machine learning. So this is what we know thus far. As we have data, we have some kind of model, a model with a lot of parameters that you can tune to decide what exactly it's going to output. Then there's the magic. So the model is being trained to mimic the data. Then you use the model and you evaluate some loss function. Okay, so let's try that. So here there's some kind of problem, a regression problem, and two different types of models have been trained, and it's really not relevant what they are here. What is being plotted is the prediction error of the data of model 1 and model 2. And so the loss function here is the sum of squared errors, so the sum of the squares of the errors of all the data samples. And you see clearly that in model 1, the sum of squared errors is 26 point something. In model 2, it's 9 point something. So from what we know now, we would say, okay, model 2 is the better one. But what we actually want to achieve in machine learning is not just this optimization step. So the first step we know, you learn a model from examples. But what you want is that your model will also work later on the data you haven't seen yet. And in addition, you actually want to know how well it will work. So you want a good estimate of how well it will perform on that unseen data. So this is a more formal description. It's one of the only really text slides I have. So you have a finite set of observations, your data, the features and the labels. And you have a model, and you can only measure how well it performs on that data that you have. So there's a whole zoo of models out there, and then you want to decide which of all these models is the best one. But the best, as I just said, is performing good on the data that you haven't seen yet. And here we bump into the main problem of our data. It is a finite set of data. It's not all the data in the world, and in practice, it usually just isn't enough. And that makes machine learning very difficult. So we have the world, we have our data, we select some kind of model, we train it, and then we want to know whether our model is close to what happens in the real world. So let's put this to the test. Let's not trust our models. So we're going to do the same as we just did. we train our model, we have some kind of train score, but then we have a bit of our data that we have set aside. So our training algorithm has never seen that data, and we use our model again, and we get a second score, which we call, in this case, a test score. So if our model training worked well, then these two scores should basically be the same. Now let's go back to our example. So now it has been extended. The plots at the top now do not show the prediction error on the train data anymore, but on the test data. And the losses at the bottom have been expanded with the test losses. And what do we see now? In our model 1, which we first thought was the worst model, we see that the test error is closest to the train error. Whereas in our model 2, which had a very low train error, the test error is much larger. So now we can decide, actually model 1 was the better model. So what happens? And where does this gap come from? So this is a story that I usually tell my students. It's a story about Bobby. And Bobby is a child, and his mom is making cookies every Sunday. And Bobby has a scientific mindset, so he says, okay, let's make a table. Every week I will taste one cookie, I will count how much chocolate is in the cookie, and I will write down how good it tastes. And then he makes a graph of that, and he says, okay, I'm going to use this data to predict in the future how good my cookies will taste so that I can count the chocolate chips and I can take the best cookie. And the blue line is what he comes up with based on his data. Whereas the black dotted line is what we would intuitively think is a better answer. So what happened? Bobby really tried to match his training data. But in the background, in the weeks 5 and 6, his mom had forgotten to put the sugar into the cookies because she had actually mixed up the two jars and she put salt into the cookies instead of sugar. So that's where they tasted really, really bad. So what happened here? There was some information that was really important for deciding the taste of the cookies, but Bobby did not have that information. That is one of the problems that often occurs in the data. There's other problems. Your features may contain noise, your labels may be inaccurate, so there's all kinds of things that could be wrong with the data. Now the problem here is that Bobby really tried to match that data. And that is sort of the core of the most important difficulty in machine learning. And so let's make this a little bit more, say, mathematical. So you have data that is being sampled from a sine wave with some added noise. So the sine wave, the green curve, is the ideal world. The blue points is what you measure. So in the real world, you do not see the green curve. You just have the blue points. And you fit a model, and now we have a model with a complexity that can be tuned. So if we make the model really simple, first horizontal line or a straight line with any angle, we see this will not work. So these models are what we call in machine learning terms underfitting. They are not complex enough. They cannot even approximate the training data, and they can definitely also not approximate the ground truth. So let's tweak the knob a little bit further, make them a little bit more complex, and then you get these kinds of plots. So the model on the left now is already getting pretty close. The model on the right is a perfect match to the training data. It's a Bobby model, but we see that it's really far off from the green ground truth curve. So what happens on the right is what we call overfitting. So to get a good model, you need to be between these different types of complexities. So the very simple models are too simple. They cannot solve the task. But the very complex models are so complex that they really try to fit the training data and all the noise in the training data, and therefore are also not good. Now, almost all machine learning models have a number of extra knobs that you can use to tweak the complexity of the model. And in the general sense, this is called regularization. And this is very important. So we have these 4 different models. How do you set these extra knobs? And we call these extra knobs hyperparameters. Because remember, in the real life, you do not see the ground truth. You do not see the green curve. You only see the data points and the red lines. So what do? What we just did before, we always keep a part of our data separate. We call that the test data. And if we then plot the training and the testing error for the different levels of complexity, then you see that the more complex the model, the lower the training error, but the testing error at some point goes up again. So normally there is a minimum, so you can use your testing data to decide which is the right level of complexity. And then you iteratively you tune the hyperparameters, because usually there's multiple to optimize an optimal test score. But now we have a problem, because now we have used our test data to optimize a model. So again, we can be mistrustful of our test score because it's already been used. So what are we doing? And normally we are splitting up the data in 3 sets, one to train a model, one to tune the hyperparameters, and one set that we don't touch yet. And once you've decided on the optimal hyperparameters, then you don't need the validation set anymore, because the name of that middle set is a validation set. You don't need that anymore, so you can put it together with your train set, retrain the model on that bigger set using the best hyperparameters that you found, and then use the test data to get to the test score. So this is very important in machine learning, to always do it that way. Now, another very important thing to know is that more data always helps. So in this case, we've used the most complex model from the previous plots. So it's repeated at the top of this slide. So this is 3 times the same model, once trained with 10 samples, once with 15 samples, once with 100 samples. And we see that with 100 samples, our model actually approximates the ground truth really well. So more data will usually help you, if, of course, the data is good quality, but we will come to that later. Now, there's a lot of problems there, a lot of trade-offs to make, because each of these sets, they have sort of conflicting, or in part conflicting requirements, because each of these sets must be large enough. The train set must be large enough to avoid overfitting. The validation and test sets must be large enough to give a good estimate of the model quality on data we haven't seen yet. So your total data set is being split up into 3 batches that all need to be large enough, which obviously is a conflict. Now, in addition, each of these 3 sets must be representative for the data your model will be used on in the real world. And representative means that both like the probability distribution of your features must be similar, and that of your labels. So if you have like 3 classes and your training set contains an equal number of each of these 3 classes, whereas in the real world, 1 class is going to be very rare, then your model will learn the wrong things. So the data must really reflect what you want your model to learn. And the same conditions go for the validation and the test sets. And in addition, these 3 sets must all be independent. Because otherwise, if your train data already contains some information about your validation and your test data, then you're again cheating. Then your train and test scores will not be good or representative. Okay, so then we come to the data, which is obviously crucial in machine learning, because there can be a lot of problems. One of the main problems is that you just do not have enough data. What does not enough mean? You want to learn a certain desired relation. Someone had an echo there. So you want to learn a certain desired relation. That relation can be simple, but it can also be really complex. If you want to learn a complex relation, you will need a lot of data. In addition, your data needs to average out all effects that are not relevant. For example, if you want to classify between family cars and sports cars, you just go sit on top of a bridge, they take a lot of pictures of cars, and it just so happens that red sports cars are fashionable. So you will have a large fraction of the sports cars images that are red. What will your model learn? If I see a red car, there's a larger probability that it's going to be a sports car. That is probably true in real life, but it's not really what we want our model to learn. We want to model to learn to distinguish the cars based on specific features like the shape and the model and whatnot. So that is what is averaging out irrelevant effects means. What also happens is you have incomplete information, and that is the Bobby cookie example. So there was this one bit of information, the salt instead of the sugar, which was crucial, but Bobby didn't have it, so that just messes up your model learning. So if information is missing, typically you will need to think how you can measure additional information. The data will most often also be inaccurate. If you do measurements, there will be noise, there may be mistakes in the labels, there's all kinds of ways in which data can be inaccurate. And then the last bit, and that's also a crucial part, has been in the media quite a lot recently, is data bias. And so I'll just introduce this with some innocent examples. These are examples from a blog where they discussed or where they analyzed image classification or detection models. Well, actually, these are models that can generate a caption underneath a picture. And so at the bottom, you see the caption, a close-up of a lush green field. And on top of that, this model can generate tags. So things that are relevant in this image. So what do we see? We see a picture of a misty green landscape with a road and some poles at the side of the road, but the model seems to see sheep there. There are no sheep, but it's mostly green and there are whitish things, so the model thinks, this might be sheep. Second is even worse. Now it's cloudy hills. It's like a Scottish or some kind of British landscape, or maybe New Zealand, a typical place where you might encounter sheep. So what has the model learned? It has learned from the context instead of the sheep themselves. So it has learned that sheep usually occur in this type of landscape. So it sort of guesses, if I see this kind of landscape, there's probably a sheep somewhere behind the corner. That's what we do too, but again, it's not really what you want a model to learn. A second example is really weird. So in this landscape, which is really not African or anything, the model seems to see a giraffe. The people from this blog analyzed the data and they found that there was a too large fraction of giraffes in the dataset. So again, something is wrong with the data. The third example, they did some weird experiment. They said, okay, let's take a picture with sheep and paint all the sheep orange. And what do you get then? The model thinks there's flowers in the field. Because the model has learned orange things in the green field are probably flowers. It's again not looking at how these things look, so not at the shape of these sheep, but at the colors. And the last example, this is really weird, is a picture of goats in a tree. I don't know how they got there, but the model thinks, okay, this is birds flying in the air, or it's giraffes standing next to a tree. So the model has never seen anything like this. And so it's not able to generalize because it has, again, not learned the shape of the objects, but the context. And so this is to do everything with data bias. So the bias in this case is the fact that sheep are most often found in green surroundings and ice bears in white landscapes. And so with the techniques we have now, you should have sheep in white landscapes, on beaches, on the sea, in top of a tree, in all kinds of situations, in order for the model to force the model to focus on what a sheep looks like and not where you find them. And so here the bias is that the data is not representative for the real world. So there was an over-representation of giraffes, so too many giraffes in relation to the real world, and well, you sort of get the idea. Now, this is kind of funny, but it becomes less funny if you start using these things in real-world applications. This was a very early, 2016 is old in this world, example of face detection in China. They wanted to build a criminal detector. And they trained this model with two sets of data. The criminals had mugshots from right after their arrest at the police office. That's the top row, and you see these people are really not happy. Well, you wouldn't be if you'd just been arrested, right? The bottom people are employees on their first day of work. So they are like really proud and happy because they have their picture taken for the company website. So what did the model learn? Well, if the corners of the mouth are pointing down, then it's probably a criminal. And if the corners of the mouth are pointing a little bit upwards, it's probably not a criminal. Sounds really stupid. But this type of mistakes happens all the time. Another type of bias is what we call historical bias. So in the previous examples, the data set was collected by the researchers, but in many examples, and this is one type of application that is currently being explored, that is a machine learning algorithm to pre-filter job applications. What does that use? Well, the history of recruitments of job applications. In other words, if we see a CV of a female person in the past, how many times has a female person with similar properties been hired, or a male person? Same for white people and people of color. Of course, you see it coming. So if there has been discrimination in the past, then discrimination will end up in your model if you don't do anything about that. Another recent example of historical bias, given the COVID situation last year, the UK students were not allowed to do their exams. So what they did was extrapolate or use a machine learning model to predict what their grades would have been. Now, if that data set is biased, and that was biased, so the results would be really negative for people who actually could have done really well. And so historical bias is really a huge risk. This is again an example. This is a very recent paper where the model really learns to mimic patterns in the data. Past examples also, if you try to make a chatbot and you train it on past chat data or on Facebook data or on Twitter data, what will come out is racism and discrimination and a lot of swearing and stuff like that. So you don't want that. Okay, so we've talked about models, we've talked about data. The third element is the task that we need to solve. And of course, these things are connected. So when you start with machine learning, okay, which model should I take for my task? So do I need a complex model? Do I need a simple model? So which things do I need to take into consideration? Now, the first bit that you need to take into consideration is the variability in your data. Because a model, as I said, needs to be able to average out all the things that are not important to solve your task. If you want to have a model that has an image, which is basically a bunch of pixels, a huge amount of pixels as an input, and as an output, it needs to say, is there a hand in the picture, for example? That is a really complex transformation. So this is really not so that is a really complex transformation. So you will need a complex model, and you will, as a consequence, also need a lot of data. Also, in some cases, the relation between your data and your output is rather simple, like the examples I showed in the beginning. In some cases, it's a really complex nonlinear relation. So even with simple data and with not a lot of features, some tasks are really harder than others. because of the complexity of the model. But we've also seen about overfitting. The more complex the model, the more easily it will overfit. Or if you need that complex model, it means you will need more data. So this is sort of the field where you need to be. And in the end, you want to find the least complex model that is capable of solving your task to avoid exactly the overfitting. So there's a number of things that you need to do because everything is connected here, and it's really easy to get lost in all the different options that you have. And so the first thing is to really think about how you set up your experiment. Data is crucial. All the possible problems with the data that can occur, you have to think about that upfront and make sure that your experiment and so your data tries to avoid all these problems. Second thing is try to make your task easier. If you have noise and if you have an algorithm that can remove it, please use that algorithm. If you can do something useful with outliers or with mislabeled data, please do, because any noise and inaccuracy that is in your data will make the task harder for your model, so you will need a more complex model. And a third very important thing is, especially if you're a beginner, so try to have a good baseline. How far do I get with a simple approach? So in simple tasks, that will be maybe a linear model. If you do complex image processing tasks, you will probably first try some standard model that is available through common tools and see how well that does. So try to make the problem simpler. That is where a lot of that insight needs to be. So I told you domain knowledge, critical thinking. So one of the things is splitting the data. I told you about the requirements about train, validate, and test set. So you need to understand your data to do that well. Second thing is pre-processing, removing noise, etc. A third thing is, well, maybe I can already, I know a few transformations of my initial data that will make the problem simpler for my model. And that is what is called feature expansion. And there's also a whole field of research there, depending on the type of problem you're addressing. And then there's this last block at the bottom, augmentation. I haven't told you about that yet, but in many cases, you can sort of create additional data by doing useful variations to the data you have. But useful here means that the result is still realistic data. So again, you need to understand your data and your problem to be able to do that. So this is the big bulk here that is in the previous slide mentioned as try to make your task easier. Okay, so this was really a bird's eye view of some of the most important concepts in machine learning. Now, as a last message, I wanted to give you some advice in getting started. I've been teaching machine learning for many years now, and this is what I see the people do. So they use some model because they want to try a certain model, because they've read about it in a blog or in a paper. They use some model on their data. They look at the test score, and it's not good enough. They're disappointed. So what do they do then? They couple back. They change many things at a time. They look at the test score, and they're disappointed again. And then, if they're students, very often this goes on for quite a while. So they get stuck in this loop for a long time, and then they get frustrated, and they tell me like, this is not realistic. You're asking us to do so much work, and it's not leading anywhere. Obviously, what I tell them is not this. So we come to what I do tell them. The problem is, of course, did they listen? So in summary, these are all the things you need to take into account. So you have certain requirements for your data. It must contain enough information, it must be representative, there must be enough of it. So you really have to understand the data and the difficulties that are in your data. So analyze the data really thoroughly before you start. The second is the labels. The labels define what you need to do with the data. They define the task. Again, there can be some problems, and of course, they must be sufficiently accurate. Then there's a part of making your task easier. So basically what you do is you take your original data, you do some cleaning, some transformations, compressions, whatnot, and you end up with a bunch of numbers, features that you will feed into your model. So again, there's a lot of thinking involved there. And then the model itself, each model comes with certain properties. Each model has its strengths and its weaknesses. So you must really understand your models and the hyperparameters that come with it in order to be able to understand what might be going wrong. So that's the first bit, and make sure that you study, that you know what you're doing before you start. And then the second bit is try to follow a scientific approach. So after that first disappointment graph that I showed you before, you really have to analyze. Analyze the mistakes your model make, analyze the gaps. So I told you there can be a big gap between train and validate, or there can be a small gap. If there's a big gap, try to understand why. Make plots, make visualizations, look at your data, then list up a number of possible causes why your model is not good enough. Select one that is, in your view, the most likely one. Change one thing in your pipeline. That is your hypothesis, like if I change this thing, it will be better. Then evaluate the result. If it's disappointing, don't stop until you understand why your hypothesis was not correct. So find an explanation first before starting the analysis phase again and try to do better. And so the more thinking you put into that, the more understanding you put into that, the less work you will have and the less frustration you will have. So this is a good advice. I give this to my students before they start, so they don't always listen, but I can only give it to you as well. Now, where to start? Well, if you know nothing about machine learning yet, start with the studying bit. Learn about the models, learn about your data, learn about the task, and then luckily, your life is really easy. So if you want to start a machine learning, I'd advise you to start working with scikit-learn, because that offers you most of the common traditional machine learning techniques, a lot of pre-processing, data splitting, all kinds of things you can do with the data. If you want to use neural networks or deep learning, if you need them, then I would advise at this point TensorFlow, because again, it is the most easily accessible and the best documented platform to work in. Okay, this is what I wanted to tell you. I think I'm given the delays more or less in time, so I'm open to questions.
Thank you very much, Joni, for making us aware of all of the different pitfalls that can exist in the field of machine learning. Very, very useful. So in terms of questions, I suggest people either type a question in chat or just use the raise hand function, and then they can ask the question themselves. So let's give people some time to formulate some questions. So you mentioned lots of these pitfalls. I mean, is there now a trend that people seem to be more aware of that, or are there still many blunders being made even in professional circles?
I still frequently see blunders, yes. Well, some of these pitfalls are difficult to avoid. The whole bias thing, of course, if that's the data you have to be very clever to avoid the pitfalls related to data bias. That is a very active field of research. The least thing is that you have to be aware of it and evaluate the consequences, of course. And that is exactly why also many companies are not using these advanced techniques yet in their commercial models, because it's too dangerous at this point. So yeah, we'll have to see how that goes. I still see a lot of mistakes in experimental setup. I remember a situation where class A was measured under certain conditions and class B was measured under different conditions. and the model just learned the conditions instead of the class properties. I think the example will sound familiar to you. So these things still occur frequently, well, mostly by beginners. So yeah, many people also dive into deep learning without getting a decent lecture first.
Then there's a question from Joseph, who wants to know what you think about unsupervised learning gaining in prominence or not. Do you think it will become a dominant method or not?
It definitely is gaining importance, just exactly because of the lack of labeled data. So there's more and more work where we see that if there's not enough labeled data, that you try to first get your model to learn as much as possible about the data itself, and then, so in an unsupervised way, basically, and then use what it's learned as a sort of a bootstrapping point to do the supervised bit. So extract already, already compress the information, like for instance, images. Images are very high dimensional, but there's not as many really interesting things to see in an image as there are pixels. So if you don't have enough labeled data, you can use unsupervised techniques to sort of extract the information that is there. Same in videos and in other complex types of data. So there's a lot of work going on there. Then of course you have the whole stream of generative models giving rise to fake news videos and things like that, where people are being glued basically into a movie, bringing messages that they never brought. I'm not sure whether that is very useful, but that is also, of course, a big trend. But as sort of a bootstrapping way towards more data efficient supervised learning, yes, we see a big rise.
Okay, Laurent van Veen has a question more specifically about image recognition, so I suggest we hold on to that question for the talk of Professor Pizzurica. And then Martin has a question related to the fact that, training these models is something which consumes a lot of electricity. Do you ever foresee a moment when there will be a CO2 tax on learning algorithms?
I hope so, but I fear not. It would definitely be a good idea. Even for us researchers, we are so used to, well, let's think of a cool experiment and then train a bunch of models and just for fun. We really should become more aware of the energy footprint of what we're doing, especially if you know that companies like Google have an electricity power plant next to them to provide energy for all their GPUs. That's not okay for sure. So we need to do something about that. And to Mahmoud, I would say yes, definitely.
Okay, so indeed, so the question was whether it's worthwhile to study deep machine learning first before diving into
especially because deep learning models are the most powerful models around at this moment. So they have the highest risk of overfitting. So in deep learning, typically you will always overfit. So it's even more crucial to understand what's happening, which mistakes you're making, and whether you can do something about that. So yes, definitely.
Okay, great. That seemed to be all the questions. Thank you very much for this very interesting and stimulating talk. Let's now move to our next speakers, which is Daniel Brunner from UBFC. So after a postdoc at IFISC in Palma de Mallorca, he obtained a permanent CNRS position in 2015, and then he moved to Besançon, the university there. And he's also extremely active at the interface between photonics and machine learning. And in fact, he was one of the editors on a book on this very topic. And today in his talk, he will take us to the third dimension, actually. So Daniel, the floor is yours.
Thank you, Peter. Can you hear me?
Yes, we can hear you fine.
Good. And you can see my slide?
That's also okay.
Good, great. Okay, I think I will move this. Okay, so first I would like to thank Joni also for this very general overview from a different angle, which we usually see in our meetings, more from the dangers of using the technique in terms of how to treat data and not to expect too much without having sufficient knowledge about the models. So here I will go to a hardware perspective on, yep, so what all of these new neural network or machine learning models actually mean from a hardware perspective, from the implementation. And this was already visible from the question before regarding the CO2 footprint, and is actually a perfect bridge for my topic, because I will go and get back to that as a big motivation. And in my personal point of view, I think there are big messages taken from the brain, to be taken from what is actually going on in the brain, at least in some aspects, in terms of identifying shortcomings of our hardware, and at the same time maybe giving us some inspiration of how to do it better. So as already indicated by Joni, this whole field is nothing really new. It makes certainly the biggest impact in the last 10 years. But the first kind of seminal paper in this field was actually published in '48, where from McMulloch and Pitts, with the intention to provide a logical calculus of the ideas immanent in the nervous activity. So there essentially you get this kind of connectionist point of view to computing, which ultimately speaks about the network of elements in order to implement a computing concept. And then later some publication by Hebb for the organization of behavior, where we see certain concepts like learning, or which in other words corresponds to what in Joni's presentation was, to basically adjust the model, to differentiate and to approximate your objective function and to reduce your cost function. So neural networks really are not a very new idea, and already as discussed by Joni previously, what do we actually want them for? And there the keyword is, I would say, non-algorithmic computing. So for example, the image recognition, what we've seen in various slides before, how do you actually want to characterize or classify features in an image? It's not a really easy task. And usually in computing terms, when you talk about computing, you have some input information and you have some output information, and you need to create the usually non-trivial and usually non-linear mapping between input data and output data. So for example, for the task of classification, you have, let's say, an image, and then you have a certain output class, which is supposed to be 0 or 1. And there needs to be some very non-trivial connection between these features. And the problem is that, as you can see in the bias before, you might be able to derive an algorithm to recognize a specific face, but then you just need to change the angle slightly, you change the mood, you change the age, whatever, and suddenly this whole geometric feature based, for example, techniques, they just not work anymore. So you need to find a more general approach, and there the generalization of these concepts is a very important point. So therefore, in the end, what we want to do for neural networks is to find or to approximate this nonlinear relationship between input data and your output data, using then, for example, learning techniques, so supervised learning. So as previously mentioned, deep neural networks, this is here just a very bulky explanation of what they do. You have here some input, so that could be, for example, the pixels of an image. Then you have connections from these pixels to a unit which essentially sums all of these inputs according to a certain weight. This would be here the weight omega. And the sum combined with the bias then is transferred to a nonlinear function, which does a nonlinear transformation. And then if you have a deep neural network, for example, this propagates to a second layer of neurons. So this essentially would be an artificial neuron. You have various of those per layers, and you might have several layers. And the task of training is then adjusting these weights until this whole blob of many functions and many parameters essentially creates this non-trivial function approximation between your input and your output. So this is the operation here, previously only illustrated as a, let's say, connectionist, a graph with nodes and edges. So essentially here we have this summation which is done by the neuron. This is then what you call X, could be an internal state. You have the sum according to the weights, the connections to the previous layer, plus the bias, and then you have the nonlinear transformation. And this precisely here, the omega is essentially what in this previous paper by McMullough and Pitts was essentially then basically inferred that you have this combination, and that is in the end the interconnect. So the interconnect, therefore, fundamentally, as a motivation, it appears to me, comes from the human brain. People or neurophysiologists looking under the microscope and doing first-hand drawn illustrations of such neurons, they could find this highly connected structure, and they somehow inferred this has something to do how our brain is doing actually computing. So this interconnect is actually the source of a lot of headache, especially now when neural networks are so heavily employed for computing. So it is on one side a curse, and it might be a blessing for photonics. Because what an interconnect actually is, it is taking information from one neuron, and this might be artificial or biological, it doesn't really matter, and distributes it across large numbers of following neurons, so postsynaptic neurons. So it's in the end nothing else than a high-dimensional data bus. So if you want to do this in electronics, you need to do it with some wires. So with wires, charging a wire, we all know has an energy associated, or the ones who we know as an energy associated of usually a half of CV squared. But a funny detail here is that actually the full energy deposited into the circuit is actually CV squared, because first you need half of that to charge the wire, and then you need the same amount of energy again when you dissipate it into the input impedance of a following amplifier or voltage sensing resistor, etc. So half of that is going into charging the wire, half of it again goes into dissipation and heat. So therefore the overall sum is at least CV squared. And the problem here is that the capacity in the end depends on the geometric ratio between the size of electrical wires and their distance. And that's an important point, because that fundamentally doesn't change a lot. Even if you go from 300 micrometers or 3 micrometers of feature sizes down to the 6, 8 whatsoever nanometers we have right now, the ratio between wires and gaps between them doesn't really change that much. So therefore, this entire benefit of shrinking chips is, as one might expect, not inverse quadratic with the area, for example, because the area of the components gets smaller, but it only goes linear, and that's a very unfortunate scaling. So in photonics, we have the advantage as wires, waveguides, fibers, how you want to call it, they do not have a capacity associated to them, no induction, and they can have very low propagation losses. But in photonics, because of the difference in the wavelength between photons and the Broglie wavelengths of electrons, we just have, fundamentally speaking, much larger feature sizes. So of the order of, let's say, 10 to 100 is more or less the scaling penalty. So the relevance of this painful interconnect is already really visible today, and also reflected in the question before. So around 1.5 years ago, there was some study and a popularized article in the MIT Technology Review highlighting this, and the really shocking number is that training a single AI model, and I mean here I want to make clear that this is really a competitive AI model, so that basically compares different AI architectures, etc., etc. So it's not just a simple deep neural network, it's a heavily involved optimization concept. However, that produces as much carbon as 5 cars in their lifetime. Yeah, so if you would now think of these algorithms becoming more and more popular, more and more widespread, and much of that is open source, everybody wants a gigantic GPU in their backyard and then just goes playing around. The consequences of this will be very clear, and we see it already in the energy footprint of today and the carbon dioxide footprint. Another sensitive issue here is that this leads, because electricity costs money, so this leads to privatization of AI research, because essentially to be competitive in this field by now, the the scale of models involved is actually so gigantic that the electricity bill is a significant contribution to the research costs. And while previously it was just about sharing codes and having a go, by now it really becomes an economic factor. So we therefore should do something against this really unfortunate scaling. And here, what I always find is a really nice inspiration is something which I find is best illustrated by a slide which is from Simon Thorpe. I stole that from him, but with his consent. So we collaborate in our project, and he is a computational neuroscientist, which has a very strong connection to actually, you know, biologically plausible concepts which might be going on in the brain. So here, what you see is a video, and inside this video, you will see a tiny face, which basically copy pasted inside of these frames. And I now play this video, and I hope it comes across with the right frame rate. And actually, if you see the image quality well enough, in almost every 50% or more of these images, you will not only be able to say where was that face, but also if there was a face, but also where was it. So this is really fascinating because actually the human eye has some 500 million image sensors, yet you are able to do this job with a frame rate of a couple of frames per second. So it's a gigantic amount of information. The other interesting bit is that I only told you seconds before what you're supposed to do, yet you did it basically normally with a very high success rate. And this illustrates that there is really fundamental things where the brain is just still miles ahead of us. And while I cannot explain how the training is done, how we can switch to such a task so quickly, I'll try to do a bit about time responses, etc. So if you just look at the dynamic response of a neuron, here on the left top from Wikipedia, the typical spike trains you can see here of activity, they have some time scales of the order of milliseconds, tens of milliseconds. So let's assume that as a very big bullet point number for neural responses. If you now look into decision making, that then neurophysiologists have identified already a quite detailed map which zones of the human brain are actually cooperating, and many times in hierarchical sequence, meaning information propagates from one region to the next, to the next, to the next. And then by considering the propagation delays of the signal propagating through the human brain and along the optical nerve, we see that actually for such decision-making tasks, we see that we have a response time of starting at 200 milliseconds until 400 milliseconds, and here the complexity of the task, of course, is of importance. So, for example, here saying was this a human or non-human was positive after 250, then gender, famous, non-famous, etc., etc. The more difficult the task gets, the longer we need. But the importance here is that essentially this, considering the 10 milliseconds time scales, the number of regions which are involved in the brain and the propagation distance between them shows that the brain is operating pretty much at exactly the limit of its components. So that means really the information propagates through the brain like in a big dynamical system as it is, and the result is produced during this propagation. So that means all of this information propagation needs to go in parallel. There is no serialness, no temporal multiplexing of, at least in these kind of automated or intuitive, quick decision-making tasks. So the second thing I want to draw your attention to is the energy budget. So the brain is fully parallel, and it essentially operates completely at the bandwidth limit of its components, which in our case would mean if we can build transistors which can easily switch even for thermal management reasons at gigahertz rates, we should actually be able to produce a neural network, a technological neural network, having an update rate at the same speed and not at the hundreds of kilohertz which we are experiencing right now. So the energy budget here, there's some very interesting work going on where people actually used a detailed energy budget from a rat neuron and then leveraging geometric arguments like how much bigger is a human neuron, how much does that change the area of the synapses, how does that change the capacity, how many messenger molecules do I need to maintain an action potential, etc., etc. So really fundamental and quantitative considerations allow one to extrapolate the energy budget of the dynamical processes in the brain. And what we can see here is that the black line is data from a core estimate, and the dashed line is considering certain energy optimization mechanisms going on. What's really important here is that we can see that if neurons spike with 0.1 spikes per neuron per second, then essentially the neocortex will produce around, or will consume around 40% of the brain's energy, which is pretty much close to what it apparently does. If this would only increase to 1 spike per second, then it would already consume the entire energy of the brain. And if another order of magnitude up, it would consume the energy of the entire body. So there is very tight regulations going on in how much energy is there and how much is actually used for computing. And that just shows how efficient this entire organism is. So here, all of these considerations are in the paper from Lenny from 2003. So here, these are more or less the energy budgets of a single neuron. The importance here is that essentially everything goes into spiking, signal generation, signal propagation, repotentiation of the system, etc., etc. So really the essence of what we think is associated to the information processing in the brain. There's hardly anything else on, let's say, on a significant fraction going on in the brain for anything else but computing, and of course keeping the brain alive. So there's really negligible emulation overhead, and here I want to say emulation because the brain is just doing what it does. If we are emulating a neural network, we're actually not doing this. We still use computers which are very serial, we still use architectures which are not a neural network, and we therefore have energy costs which are orders of magnitude larger than they could be if one would just build a neural network out of its components and connect them via a network. So, and I think this is the way we should follow if we want to achieve the energy efficiency of, for example, achieved by the brain, which only uses 20 watts. And if what one estimates the dynamical processes going on in the brain, then actually one would need close to several petawatts of simulation power, and that actually uses petaflops of simulation power, and that actually uses a computer which uses 20 megawatts. So there's 10 to the 6 overhead. This argument is, of course, has to be taken with care because it doesn't really correspond to the real thing, but it gives you an illustration. So here's an overview of many of the special purpose silicon circuits right now used in neural networks. And for those, they achieve roughly 10 to the 12 operations per second, while the brain achieves 10 to the 14 operations per watt, not per second. However, multiply and accumulate, and this is in the end the sum and the sum product in the neural network, the summation with the weights and the previous state, costs in hardware around 1 picojoule, whereas in a synaptic event in the brain only uses 5 femtojoule. So that shows also that an operation is not really an operation. So an operation we are carrying out in silicon cannot be as efficient in implementing this entire multiply and accumulate operation as it actually is going on in the brain. So here we have another 2 orders of magnitude difference, and here we appear to have another close to 2 orders of magnitude difference in efficiency, which gets us already a quite gigantic overhead. And in my point of view, this is because we became really good in doing this, in essentially building Turing machines, for example, using the von Neumann concept, and that is essentially what drove the entire silicon hardware development. But this, unfortunately, is not at all what is this going on in the brain, and what ultimately also determines quite a lot of the structure of a deep neural network. So how does the brain do it? And for me, a big point here is the argument of parallelism, and that nothing is really wasted besides creating and propagating signal, and of course then adjusting for the learning. So the most important thing that requires is actually that a network is a network. So that means a neuron is connected to other neurons via connections. And the problem here is that this is not so easy. Whoever looked at the electrical circuit diagram knows how untrivial it is to connect several components to each other when there are many wires going on at the same time. If you now want to connect every component to hundreds or thousands of other components, you will face a gigantic challenge. So the brain is actually doing this by leveraging 2D and 3D strategies. Neurons are mostly implemented in a 2D sheet, so they're wrapped around the neurons, around the brain surface of the neocortex, the aggregated surface. Via at least a long-range connection, they go through the volume of the white matter. And furthermore, it uses something like scale-free connection topologies. So instead of connecting one to the 1,000 others, starting with 1,000 wires at the soma, at the cell body, it branches off a bit like a tree. And therefore, the branching is much more efficient. So why is the scaling problem? Where is it coming from? So for example, if you would look in 2D, you have a vector of input, a vector of outputs. Every connection, every weight, should you physically implement it and not via a serial emulation, needs some physical entity to represent this connection strength. So if you do this in 1D or 2D, you quickly get that the number of channels scales with the square root of the area of your chip. If you do this in 3D, you can allocate the input and the output in an area and then introduce a plane in which you connect each of the inputs to each of the outputs, or one input to each of the outputs. And therefore, the area scales linear with the number of channels, and the height does so too. And this is really the most rudimentary connection strategy. So this is in the end what I think as a first take-home message I want to take from this field. So in our recent work, we then studied also this concept, how can we do this in hardware? And we wanted to go ahead with another inspiration, this fractal branching, and there is essentially you have a fractal degree. How many branches do you have per bifurcation? And the really interesting here is that it scales exponentially with the number of layers. How many branching layers do you have? And here we designed a certain geometry, how actually you can decompose a complex large-scale network into something like unit cells, which are just copy-pasted and then scaled up. But I will not go into detail here. So what we used for this is a modern 3D printing approach. It's actually not that revolutionary. That process, the two-photon polymerization, is by now commercially available and actually done since 10-15 years. So you use a very high power laser, you focus it into a resin of monomers, and by two-photon absorption you actually polymerize the monomers, and therefore you can create a solid body within a liquid, for example. There's other processes, and then you remove the liquid and then you're left with the region which you have exposed to the two-photon absorption. So with this we printed waveguides, which are in the end the wires for the photonic wires for electronics, or the photonic equivalent of wires in electronics. And with this we now start printing these 3D connection structures like you can see in the brain. So here, for example, an array of 1 to 9 splitters, here with exactly the same topology, but now already 2 bifurcation layers, a 1 to 81 splitter, and you see the exponential scaling. And here we have arrayed them in a large array of 225 inputs and I think 500 and something outputs in an area of 0.04 millimeters square, around that. So just to be clear here, this is not programmable yet. It also is not yet completely integrated in our systems. But if you would look at normal standard silicon waveguide based circuits, then on this area you could, same footprint, you could implement maybe 4 or 5 connections. So this just shows the power of 3D if you want to build these direct networks. We characterized them to a certain degree and found that even for this, let's say first demonstration, proof of concept, the losses were actually quite low. So we had propagation losses of only 1.1 dB. we had coupling losses, so at these bifurcation points of 1.7 dB. And by now we have reduced this further by another order of magnitude using some architectures which are not yet published, but they're in preparation. So instead of these very high dimensional full connectivity kind of ideas, we want to also demonstrate a first functionality. So in deep neural networks, there is a subfield called convolutional neural networks, and actually it was shown that this is something also going on in the brains of mammals. So the receptive field of the eye is by different areas in the brain continuously evaluated against certain generalized or canonical geometrical features. So, and this is done by, for example, in convolutional neural networks, is reproduced by convoluting your input field with different Gabor filters. So here is a certain show of, a set of Gabor filters with different orientations. They are Gaussians multiplied by sines or trigonometric functions. And what it does, it highlights different features. So if, for example, here this is a Chinese symbol with a lot of curvatures, etc., etc., and you can see that for different filters, different features are highlighted. Horizontal bars, like here, more vertical bars, such as here, a little bit of a different inclination here, both of them combined here. So basically, Gabor filters highlight generalized geometric aspects. So this we've implemented in our 3D photonic waveguides, where we have created 9 filters in a 3x3 unit cell. And how we have done that is essentially at the bottom here, you would see the input pixels of an image, and they would be routed to one output waveguide according to a certain topology. So this filter here, for example, that is our filter 2, yeah, but rotated. So here, the horizontal, the two lines, the two vertical lines, and the black line in the middle would route to the output. And then, as we go on, every output is routed to a different connection topology, and by that implementing these different Gabor filters. Those, of course, you can then print in an array, and with this we can imagine, or we can envision that in the future we essentially use this as the first layer of a convolutional neural network, for example. And the important part here is that there is essentially optical propagation losses, are of course a source of energy losses and dissipation. But there's no switching going on. Essentially, the visual input would just propagate through the network, pretty much as activity propagates through the brain. There is no active switching between different routing channels, between different memories, etc., just like in today's hardware. But information simply propagates against on the wave propagation, gets transformed. And I would say this is the general vision which I would like to pursue, and which I think is the most promising in terms if you want to go to really low energy consuming neural networks. So to really achieve a breakthrough, here I focused on the parallel networks, and I think this is very important. Of course, if you want to build a photonic neural network like this, we need the neurons. And optics is always known to be great for that, information transduction, information propagation, but it's always been critically eyed using nonlinear transformation for good reasons. But I think there's some really interesting achievements lately. Then, of course, what needs hardware motivated learning. I think it's not very promising to simply take exactly the concepts which were developed for the current streak of neural networks, full differentiability, no noise in the system, error backpropagation concepts, etc., and just hope that these will be one-to-one, we will be able to map those on actually a real network architecture. So I think if we want to reap the benefits of really building a neural network, we will also have to learn more from the brain. How is the brain actually learning? And finally, a really important ingredient for such networks is that they are analog. And therefore, a big question for me is what happens to noise. For example, if you make the network deeper, does it accumulate? Does it get squeezed? How is this behaving? And here we have a model for linear neural network, and I'm really happy to say that now we've extended this for completely trained deep neural network nonlinear neurons, and we found really amazing results that we can identify very simple conditions where noise essentially does not propagate. And here just a very quick summary, and now the registration deadline is over. We have a conference on emerging topics in artificial intelligence in San Diego. This is the 2020 commercial. Its announcement. 2021 is happening again, but if you are interested, maybe there is again virtual participation, and it would be great to see some of you. And thank you very much.
Okay, thank you very much for this very nice talk. There is some discussion going on in the chat about whether the brain is actually a parallel system or not, because people cannot do several difficult tasks at the time. Not sure if you have anything to mention.
I think here it's important to differentiate between different tasks at a time and information propagation within one task. So I think that within one task, information propagates in parallel is undisputed. Between different tasks, to carry out different tasks, I think what might be more important there is arguments of energy consumption, because in the end, the energy consumption of the brain under load or almost doing nothing, besides using some pathologies and sleeping, is completely constant, or varies very little. And what you see is that actually the energy consumption is then routed around. And some neurons, they then, if they're heavily involved in processing a task, their spike rate increases to 100 spikes a second, for example. So that would just mean that you would fall in a glucomic coma if, I think, too many regions would be active. And I would rather think it's a energy argument rather than a topology argument, which limits us in terms of parallelism for several tasks. But I'm not a neurophysiologist, so please.
Okay. And Emmanuel wants to know whether you think that in the future our smartphones will contain hardware specifically meant for AI applications, and whether that hardware should also be backwards compatible with non-AI functions, or you should have a combination of both. So what's your vision there?
I mean, that the cell phones already do co-processors, include co-processors. I think certain new generations of the ARM processors, they have special cores for AI. New Apple chips, they all include AI cores. So that is not necessarily only for the cell phone, but also for the computer. So I think that for sure is happening already. If it will be photonic or not, I think this will depend a lot on integration, etc., etc. Backward compatible, I think they should be interfaceable for sure, and maybe in both directions. So there needs to be communication going on between both kind of worlds. And in this aspect, I think compatible, but I think compatibility in terms of that they could execute classical algorithmic problems, I think I would be more careful, because then you fall in the same gap. AI processor would be great to do AI, but I'm pretty sure it would be bad to take the square root of a very large number. So
sure. Yeah,
that's what I think.
Thomas wants to go back to slide 17. Could you explain the different connection topologies again?
Damn it. So this is slide 18. Slide 17 I have suppressed, so I'm not quite sure which slide you're referring to.
Thomas, can you perhaps unmute yourself and comment which slide exactly you meant?
16 indeed. I didn't see that 17 was hidden.
Yeah. So 16, this is just, let's say, this kind of fractal routing. It's also something which is, for example, considered by Corbena-Boine in the electronic chips. It is simply that you, you do a kind of scale-free fractal branching of connections. And the only thing we reinvented potentially here is that if you do straight connections, then you have a lot of wires which are crossing. So let's say this is the top view of a 1 to 9 splitter. If you want to connect the black splitter with the red splitter, then these two wires, if everything is straight, they would cross, and therefore you have crosstalk. At this central position, you would have 4 wires crossing here, 2, 2, 2. So you can induce chirality, curvature, in the XY plane, and then essentially you remove the elliptic degeneracy from these crossing across the horizontal and vertical lines, but not in the center where you have the diagonal crossings. And for that, you also need to induce some chirality in the Z dimension, and then you can design these kind of in semiconductor physics you would call them unitary cells, and then you just copy them around like 1/4 of such a structure. Is this what you were referring to?
It was, yeah, thanks.
Okay, thank you very much. I'm afraid in view of time, we have to stop here. So let's take a 10-minute break and then we'll reconvene at a quarter past 3. So see you all then. Bye.
Thank you. Bye-bye.
Good afternoon. Welcome back, everybody. Our next speaker of this afternoon is Thomas van Varenberg of Hewlett-Packard Labs. He actually got his PhD in Ghent University here, but afterwards went to the States to join HP Labs in Palo Alto. But since about 2 years ago, he's now back in Belgium to expand the research of HP in Europe, and he will be talking to us about the industrial perspective about AI and silicon photonics. So Thomas, if you're ready.
I am. Thank you, Peter. Let me know whether you can hear me well and see my slides.
Everything's fine.
Cool. Yeah. So thanks a lot for the opportunity to let me present here. I'm going to talk about the research that we do in labs, but before I dive into that, I quickly want to mention some work I recently heard of and that I also think is relevant for the topic of this workshop. And that is that indeed silicon photonics is actually going to be pretty good for AI or for neural networks in general. Why is that? It's because silicon photonics is this energy efficient links that are very cheap to produce because you can use volume fabrication, and every link can have a very high throughput or bandwidth. And it turns out that if you put in those silicon photonic interconnects in current compute resources that are available, like GPU clusters or HPC systems, high performance computing systems, because of the very predictable workloads of AI, when you train a neural network, you can actually really predict how that flow will use the resources. Having broader, thicker bandwidth links allows you to reschedule the way that you train, and instead of, you can actually make a distinction between data parallelism during your training or model parallelism during your training. And by having access to silicon photonics, apparently in a study that will be published soon, there's a possibility to go hybrid and really optimize how many resources you use to train, how many CPU chips you use for one model, and how many models did you train in parallel on different parts of the data set. So that's great, and actually the performance benefits that you can get are on the order of like a 10x or something, just by having access to this novel link. But as I mentioned, that's actually not the topic of my presentation. I want to talk about things that we do in HPE. And the first thing that I will talk about is, again, how can we use silicon photonics for AI-related applications? I'm going to not really talk about machine learning application, but talk about something that is a little bit related to this, in the sense that I want to discuss how we can use this technology to solve combinatorial optimization problems, specifically the ones that are NP hard. That is like a difficult word to say, that they scale exponentially badly as a function of problem size. Like there's this typical example of a traveling salesperson who needs to visit a couple of cities and wants to rank them in the optimal order to reduce the total time that this person is traveling, or the total sum of the flight tickets. If you have 5 cities, then there's 12 ways of ranking the cities, so that's pretty easy to do. If you have 15 cities, then there's already 40 billion possibilities, so that's the exponential scaling. If you go to 100, it really is impossible to do this manually. Even exact algorithms start to fail at that point. And so you need heuristics. That means that you need algorithms that can actually give you best guesses for the given compute time that you have available. And so I'm not going to talk much about it, but there's like really a lot of applications for this in industry. And the main thing that I want to prove or explain is that actually we need heuristic accelerators. That means that we need specific hardware to solve those heuristic algorithms in an energy efficient and fast way. We have a little bit of prior research that we actually can refer to, in the sense that some people thought that this application was a good one to use quantum computers for, specifically quantum annealers. But then you had some other researchers who made a classical optical system, and the comparison is the thing that you can see here. So the top graph is the success probability, that is for a given combinatorial optimization problem, what is the chance that you can get the optimal solution as a function of problem size. And you see that the chance is way higher for the black line, which is the optical system, than the colored lines, which is the quantum annealer system. And if you then also calculate how long that it would take to find the optimal solution, if you retry over and over again, then you see a similarly bad scaling for the quantum annealer. So that's actually a lot of incentive for us to look into this. So what have we done in labs? We've developed two different platforms. One is an electronic one, and the other one is the optical one. I'll first explain the electronic one because that's like tutorial-wise a bit easier to understand. So yeah, how does this work? The thing that we implement is a Hopfield neural network. So it's a neural network, so it's related to AI, hence the connection. And the idea is that you actually, there's a way to map combinatorial optimization problems into a matrix of a Hopfield neural network, and that Hopfield neural network consists of an array of binary neurons. So the neurons can either have two states, either 0 or 1, or +1 or -1. And then you have a matrix multiplication, and then a feedback loop that sends out the outputs of that matrix multiplication as an input to the binary neurons for the next time step. And if you look into this, actually what you optimize is like some kind of a figure of merit that is quadratic in binary state variables. You take the derivative, you get the equations of motion because of that, and you kind of actually do an algorithm that is representing gradient descent. So at every step you calculate, following the gradient that you have for the figure of merit, what should be your next position if you want to improve your solution. So we were able to map this in hardware by replacing that matrix vector multiplication, the connections with a matrix containing memristors. A memristor crossbar is the name that we use for that. And a memristor, for people who don't know, is actually just a tunable resistor. So you can program it and it can have different weights. So a single device can actually represent different levels, and because of that it's also more energy efficient because you can represent information in a denser way using less hardware. And then there's some digital feedback loop that you can also see on the slides on the bottom left. I'm not going to explain too much details there. As the pictures on the middle of the slide show, we actually have a hardware chip in the lab with a control board that we've used for measurements, and so I'm going to dive into that soon. But some things to remember: this thing is analog. It does contain noise intrinsic because it's analog hardware, and because it contains noise, it's a probabilistic system. So talking about that, so the noise actually can be a beneficial thing because this thing is supposed to be implementing gradient descent. So that's an algorithm that is known to get stuck very easily in local minima. Because you just go down in the energy landscape and you hit the first local minima that you see. And so if you have noise, then you sometimes will make a stupid move. And if you have enough of those stupid moves, you actually are able to jump out of the local minima over an energy barrier and go into another basin of attraction, and so on and so on. And by doing that in a clever way, you're typically able to find global optima. And so that's what you also see in this experimental result, and also like with some simulations to show that we understand what it's doing. We see the cost function as a function of time of a couple of different trends. You see the black line where we had a little bit of experimental intrinsic noise, but it wasn't very hard. And you see that the cost is actually very soon saturating and it gets stuck and it doesn't reach the optimal noise level. If you do something clever and if you have noise, initially you have a lot of noise and then you taper down the level of noise that you have, then eventually you will indeed be able to get close to the optimal solution. And if then your noise is small enough that you don't jump out of the optimal solution, then you will stay there. So that's something that we can do using a technique called simulated annealing. If you have fixed noise and it's too strong, then you get what you see with the blue line. And that's just like, you will never be able to see the global optima either. So there's like really a trade-off there. So we did those experiments, and then we took the data from our experiments, did some simulations to benchmark how long it would, if you really fabricate a chip at like a demonstrator level, how fast it would be, what power it would consume, and how many solutions for such a problem you would be able to generate per second and per power. And we compared it with digital solutions like GPUs, CPUs. We also compared it with the optical solution, which is the CIM, and we also compared it with quantum annealers. And I'm not going to repeat every number on the slide, but overall, if you do the math, you see that we actually can do 10,000x better in the energy efficiency metric compared to the digital solutions. So that's pretty promising. Little disclaimer there is that this is just for a single chip. Single crossbar, I mean. So if you want to solve bigger problems than what the crossbar now would be able to handle, then you actually would need to interconnect them, and then you would lose a little bit of the efficiency. But given that we have so much room, so much benefit over the other solutions, we actually think there's still reason to look into that and continue this line of research. So what's next? We've actually also looked a little bit more into quantum annealers, how they work. So the thing that I explained on the top left of the slide, it's simulated annealing. So that's what we've done before. Quantum annealers, they work slightly differently. They use quantum tunneling to tunnel through energy barriers instead of using noise to jump over them. But if you look at hardware implementations of those systems, and you see that they typically do something different. They work with adiabatic annealing. So they start with an easy energy landscape. They put their system in the global solution that they know in advance that exists. And then they slowly change that energy landscape to the one that they care about. And if they do this slowly enough, in the quantum case, you're guaranteed that you will stay in the global optimum. And so that's something that they do there, and they get some results with that. And the idea that we had is, and also some other groups have this, is that you actually can do this in the classical domain as well. And another reason to look into this is also because if you look in real life applications, such as the ones that you see on the top right of the slide, sometimes you solve a system, the situation changes, like for instance, a traveling salesperson problem, weather changes, you need to adapt the route based on a storm somewhere. And you can intuitively think that using the previously found solution actually would be a good starting point for the next one. And so that's also something that we could do with this adiabatic annealing. So we looked into this. And again, this is in the middle, we show an experiment that we run on our chip, where we go from problem P1, that's the starting problem, we solve it, so we're here. And then we want to go to problem P2, which is what you see here. We want to reduce the energy as a function of time. And because we don't have a quantum system, because we work with analog computing, we need to inject a little bit of noise, but we have a certain transition region between the two, P1 going to P2. And by doing this slowly enough, we actually see that we can indeed get pretty good solutions as well. And so then we compared what is the probability to get the optimal solution for different problems, comparing the quantum-inspired algorithm versus the direct solution where you just solve P2. And you see that there is indeed an advantage of starting from the previous problem. So it's a moderate improvement, but it's still something relevant to look into. And given the context that I explained before about like changing problem situations, is actually something that is beneficial. So that's all for that hardware platform. The other one is silicon photonics. Just in a nutshell, it's kind of following the same principle. You have again an array of neurons. This is a top view of a chip, which are supposed to be binary states at the end of a run. Then you have a multipath interferometer, that is a connection matrix where you encode your matrix. You have a feedback loop. The matrix we encode using MZI interferometers, using phase tuning on chip. And then you need some nonlinearity to have bistable nodes. What we use for that is microrings. Those microrings have resonance frequencies. That's what you see here. If you come in with a laser wavelength very close to a resonance frequency, yeah, your resonance frequency stays where it is. But if you ramp up the power, some of the lights will change the material properties in the ring. And because of that, your resonance frequency will shift. And because of that, you get a nonlinear behavior of the output versus the input. So you get this type of S shape that you see here. And this S shape, you can intuitively think that there's two states, like a +1 state and a -1 state. And that's how we can actually map, use microrings to represent binary nodes for this type of system. We did this in simulation. And indeed, like here, you see that we ramp up the power. During a run, we get two states at the outputs, and we see how the energy that we want to minimize fluctuates for different runs as a function of time. And in this case, we don't start with the system in the state where it's already bistable, but we start in the state where it's just like still, you just have random noise. But we have some kind of a gain mechanism that is slowly ramping up. We have a programmable loss mechanism, and the moment that this gain is touching the programmable loss, then your system is hopefully oscillating in the lowest loss state. Okay, so what are the advantages of this topology? This is actually better than the initial optic system that I started from when I was explaining how people have done combinatorial optimization using classical hardware before. They use OPO systems, which are a bit harder to make on chip. We use another mechanism. We can use different nonlinearities that gives us a bit of flexibility, and we can therefore probably also do this at higher speeds and at lower energy consumption compared to the electronic platform. And one of the advantages would as well be that maybe at some point we would be able to process optical information. But downside, obviously, because we work with photonics, we have a bigger footprint and the platform is a bit less mature. So that's a lot of information already, and I'm going to add even more information by talking about a completely different topic, which is from a designer perspective in an enterprise in silicon photonics. I want to explain how we think and use AI techniques recently. That's work done by one of my collaborators, a couple of collaborators, but the slides that you will see are made by Sean Houghton. So yeah, some credit to him for that. The use case, we actually use it for multiple use cases, but the one that I'm going to explain in this part is silicon photonics. We want to make it dirt cheap. We want to be able to couple lights on a chip. For that, we use grating couplers that couple light from a waveguide out of the chip into a fiber mode. Typically, insertion losses in simulation that you can get are something like this, like -1 dB. And then what do we do with this thing? We actually couple the light of that grating coupler into some kind of connector because, oops, we want to, yeah, pluggable connectors are way more efficient or like better for maintenance costs of networks compared to gluing your fiber on a chip. So that's why we are looking into this. But the take-home message is as well that if you have light that scatters off angle of your grating coupler into the connector, then you actually need to compensate for that off-angle light somewhere in your design. There's multiple ways of doing it, but it's always a mess there. So consequently, I got a lot of pushback from the designers of the connector, the mechanics there and the optical system. And they asked me, can't you just make a grating coupler that shoots light vertical? So yeah, that's the question. Can we make this thing vertical? And then people who know something about silicon photonics, they actually should realize that this is a very, very bad idea to do. Why is this a bad idea? It's because if you just derive the phase relationships between different scatterers on chip and you derive what the phase accumulation is to have light propagating vertically versus light that the phase relationship for light that goes backwards, then you see that those phase relationships actually coincide. Consequently, if you just do this in a naive way, you get minus 10 dB of loss. And you get really a lot of reflection. So it's completely, it's a pain. You wouldn't want to use those components. And so what did we think? We thought like maybe we can actually use a different technique. We can use inverse design, more specifically the adjoint method to optimize this. This is a gradient-based optimization method. So you start again with an initial guess and you want to find the global optimum. The adjoint method is just a clever way of using computationally intensive FDTD simulations where you run your fields, you calculate a figure of merit, and then you want to calculate a gradient. If you have n variables, you will need to, in a stupid way, you would have to find the difference that gives you n plus 1 evaluations that you would need to do of the FDTD simulation. A joint method allows you to do one backwards propagation, similar to backpropagation in neural networks. And so with two simulations, you can get n, the local figure of merit, and its derivative. And so that's pretty efficient. And this is a slide showing how this works. You see a grating design, you see desired field profile, you see the field shooting out of the grating under a certain angle. This is not our work, but this just shows the technique. You see that this is behaving as it should. Actually trying to go to the next slide. So we applied this technique to the specific case where we wanted to shoot light vertically. So here you see field profiles. You can really see that light is indeed shooting upwards. We did this for two platforms. One is using silicon, single layer silicon gratings. Another one is using silicon nitrides, focusing layers on top of the silicon grating. And we get actually pretty good insertion losses and also usable bandwidths. So that's actually promising. And at this point, last week we got back our wafers and we're now measuring those, and hopefully we can get results that correspond to those simulation results. Okay, so that's not all, obviously, because that's actually still using things in a very simple way. We want to go beyond this. And what did we do there? And disclaimer here is that the results that I'm going to show now are very, very preliminary. The use cases that I'm going to show are sometimes a bit too simplified, so don't look too much into those. We actually have more complicated systems in mind that we want to look into, but it's just like to give you an idea of what we want and what we think that are the challenges of this type of technique. So the issue is that gradient descent is very good in finding the local minima that is close to your initial guess. And so what we do in our technique or design flow, we use physical intuition, because we're engineers, we understand optics. We use some in design that is close to the design that we want. But for some cases, it's very hard to come up with such an initial guess, and you might actually have a wrong initial guess and you wouldn't know. So you want to have like a technique to know that your solution is really good, or you want to be able to sample things that you didn't think of yourself. And so that's why we go to global optimization. So yeah, that's what is explained here. Bad initial guesses give you bad solutions. I'm going to show this more with this example here. So strong red is good in this case. Blue means bad. And things that you see here is like you have an initial guess and then it goes to the best solution in this case. We use gradient descent algorithms. This is just a toy example, but it has some periodicity similar to what we have in our real-life applications. And so now I'm going to see a couple of trials to find that global optimum. And so you see your initial guesses, if they're far off, then they won't find the optimal solution. Interestingly, if you would just like take the surface of this rectangle here and you would start in there, then you're guaranteed to find this global maximum. That's like with what is it, 2.7% probability. With this gradient descent technique, we still find something a little bit better. It's actually still running apparently. Let me fast forward. So you see here we get 4%, 4.5% of the solutions get actually into the global solution. That's not many. And so instead of like throwing away the information of like RINs that are over here, we want to do something more clever and do something more holistic with this type of example. Okay, and so how do we want to do this? So I'm going to go back to the technique that I explained before. So we use physics intuition. We come up with some initial design parameters. We do our FDTD field simulation. So this is very, very compute intensive. We calculate our figure of merit. We calculate our gradient using back propagation. And then using the gradient, we update our design variables. And the thing that we want to keep is this part, because this is something that we won't be able to change too much. What we want to change is this physical intuition thing, because we think we can do better, or we should do better for difficult problems. So we keep this and we change this by a neural network, a parameter generator. So this is a generative network. And what we do in this case is like we sample from a known distribution, like uniform, Gaussian, whatever, and we train a neural network to have a mapping between those random samples and the parameters that you care about. So how does this look like? It looks like this. You have, this is iteration 0 of your neural network. You see the figure of merit, you see some random initial guesses. And then by training the neural network, what we really want to have, or what ideally would happen, is that all those samples during a single batch actually are very close to the global minimum. And so, still don't forget doing sampling. In my toy example, it's not really the case, but in real life applications, it is the case. The sampling itself is still expensive computationally, so we don't want to have too many samples during one batch. So how does this look like? I'm going to show a couple of results. Again, for my toy example. So first off, suppose we have a distribution which happens to overlap with the global optimum that we care about. So this is our initial guess. And so I'm going to run my movie again, and you're going to see flashes of the distribution per iteration, and you will see how they then gradually converge to something that is more centered around this thing. So actually you see after like 100 iteration or something, actually 60 iterations already, you're pretty well targeted around your global solution. But yeah, sometimes it's still hard to come up with an initial guess. So how do you initialize your neural network? And that's what happens here. You're far off. And even though you see that this is doing global optimization because you stick in some local optima, it's not finding the one that you really want to find. And this tells you that, yeah, it's probably going to be better to do this type of technique, but we're not guaranteed that it's going to do super well. You can then still optimize things a bit, like, yeah, this should be the next slides. You can go close, like far from the global optima, but just have a wider scan or range of parameters. And then what you get is something like this. So it's a wider distribution initially, and eventually it's indeed able to find its way to the range of parameters where you need to go. It takes longer though, so that's what's happening here. But it eventually does converge. So that's good. But then here in this case, I was still using a lot of samples, so that's computationally intensive. And so what we really want to do is actually something else. We want to be, sample a bit less. In this case, you will need more iterations, but eventually you will still converge. And then the thing that you really care about is how many function evaluations that you need to have before you end up in this global optimum. And so that's working here, at least for our toy example. So again, this is preliminary work, but people have used, and actually we stole the concept from preliminary work by a group in Stanford. They were using this for meta lenses, and using this generative network, they were able to come up with a more challenging problem, and they needed 2.5 million simulations to make this work. But they needed 10x fewer simulations than starting from random initial guesses and then doing gradient descent. So there's indeed an improvement in using your neural network approach. Then we try to apply it for our grading example. And so that's what you see here. Total loss as a function of iterations is, yeah, it indeed goes down. And so we get some good numbers. And then the maximum efficiency over one batch. So this is actually the physical number that you care about, couple efficiency. The blue line is with neural network technique. Gradient descent is this dashed line here. So we want to do better than this one. It's for an easy case, 8-degree gradient couplers. We have 20 device samples per iteration. We do see that we actually need gradient descent, but physics intuition would give you, in 200 simulations, you would be able to reach this kind of good number. The global optimum with our technique, you still need 40,000 simulations. So that's already better than the 2.5 million that I was talking about before for the other application, but I think our problem might be a bit simpler, but it's still, yeah, 200 times worse than this gradient descent technique. I do think if I compare with other global optimization methods that we probably can reduce this number with the number of simulations with another 10x, and we actually have some pretty good ideas of how we should do this, but yeah, we'll have to wait and try those ideas. Okay, so I'm reaching the end of my presentation. I talked about 3 different things that I want you to remember. First thing to remember is that yes, silicon photonics will indeed change AI by virtue of training the hardware, by having a way better network in there, and that's probably going to have some impact on what people can do. Second, silicon photonics, you can use it just like analog electronics, in fact, to outperform quantum annealers for combinatorial optimization problems. And then third thing that I've talked about is, yeah, machine learning might help us with global optimization in for photonic devices or new functionalities that haven't been explored before. And with that, I think it's time for questions. Thanks for your attention. Okay, thank you very much, Thomas. Let's wait a bit for questions in the chat, and let me ask a question myself meanwhile. So you talked about these quantum-inspired algorithms. So does that mean that there's no hope for real quantum stuff to be helpful in the future? Or how do you see that evolution? Well, yeah, so actually my take on this is you have 2 flavors of quantum computers. So one is the universal quantum computer, the other one is the adiabatic annealers. And the adiabatic annealers, I do not think, at this point, my thought is that they are not going to be useful for optimization problems that are business relevant. There's actually a lot of research that proves this. They might still have their benefits for quantum simulations, but there needs to be a technological challenge that still needs to be solved to make that happen. For the general universal quantum computers, in fact, we do think there are some algorithms that we can't do better with classical computing. For instance, like prime integer factorization. That's like one of the known algorithms. There's a couple of other ones that is just indeed quantum If you're able to make big systems with like 4 million or more qubits, then you would be able to do something that you can't do classically. But for a lot of problems that people think where it would be useful, for instance, for AI, at this point, there's actually no real reason to believe that it is going to be a benefit. I'm still interested to look into the Ising platform, the photonic platform, at the low photon number limit and see whether there are some benefits there. But at this point, I also have no idea of something that really is convincingly telling me that it would work. So yeah, I hope that answers your question.
Yeah. There's a question from Chonghua who wants you to explain a little bit more in detail what goes on in the Ising machine node. How do you make it?
Let me try to go back if my slides collaborate. Yeah. So there's one thing that I apparently forgot to copy paste a picture of my Ising node here. So I'll get back here. So what I hope, or like the main thing you should remember, is that using nonlinear optics, you can actually get this type of S-shaped things. This is like really a threshold. You can even make it bistable in a certain region. And you can map 2 different states to every branch of that S-shaped shape. And then the next thing is that this is kind of asymmetric, so that's annoying because you want to have unbiased solutions. And so the trick that we do is we put 2 of those bistable ring resonators in a coupled system with a feedback loop. And by having the feedback loop, we can make sure that the system with those 2 microrings, so like each microring has 2 stable states. You have 2 rings, which means that you have in principle 4 stable states. By having the feedback loop, you can destabilize 2 of those 4 stable states so that you have 2 and then symmetric stable states that are remaining. And so I know that's like a little bit, yeah, you probably need to see the schematic and the mathematics for this, but at the end of my presentation, I think on the conclusion slides, I do have the reference where you can see the whole mathematic derivation. So if you want to know more about this, then just check this paper here, the first one, which really dives into the details of what we're doing and why it works. But on the other hand, for the Ising nodes, you actually can do a lot of things. This is our proposal. We've also seen work where people are just using a photodiode. There are people who do this in free space optics. There's really a lot of flavors of doing this, and actually all of them perform better than quantum annealers. So yeah, maybe that also gives a bit of perspective.
Okay. Then there's a question from Ahmed about your taper design. So what about the back reflection? Is it big? Was it also included in the figure of merit?
So that's probably about this thing.
So your inverse design.
Yeah. Bummer. So apparently I don't have the figures here which show the reflection, but yes, we can. One thing you can actually already see is that we reduce the insertion loss quite significantly. So there's not too much loss that you lose when you go from the waveguide into the fiber. We still have some reflection. We have more reflection than what you would have for an 8-degree coupler, but we do know that we can reduce it over a pretty broad bandwidth with more than 10 dB. I can't give you the number at the center wavelength. That might actually be way more. But we specifically used broadband optimization to make sure that our reflection is also lower over the whole bandwidth. And no, we did not have to include explicitly the value of the reflection in the figure of merit. We could if you really care about it, but just pushing on the loss already reduces the reflection automatically, we've noticed.
Okay, thank you very much. So I'm afraid that's all we have time for. Let's thank you very much again and move to the next speaker, which is Professor Alexandra Pizurica from Ghent University also. And she's very active in topics like artificial intelligence, specifically for machine vision, image recovery, compressed sensing, these types of topics. And a couple of years ago, she was also involved in the analysis of the very famous Lam-Gods, the altarpiece here of the Van Eyck brothers in Ghent. And today she's going to talk to us more about AI and the interface with computer vision. So Alexandra, the floor is yours.
Thank you, Peter, for this nice introduction, and thank you for the invitation. Is the sound good? Can you hear me well?
Yeah, we can hear you.
Okay, I will share. I'm just trying to share the screen, but it seems that I cannot share the screen. I'm sorry. I don't know what's going on, but
Sometimes it helps if you just share a window rather than the full screen or the other way around. That might be something to try.
It is just when I click on sharing option, I don't get anything. It is just like, could it be that, oh, I'm so sorry about this.
No problem, no problem.
I just get that the sign for waiting. I cannot share the content. So maybe I need to do something else. I don't know.
Perhaps restart Teams.
Okay.
Okay, so we'll see you in a minute.
Okay. I'm sorry, I still have the same problem. I cannot share the...
Then perhaps it's an option to mail the presentation either to me or to Kamal, and then we present from our computers, and then you just tell us when to advance the screen.
Okay. I also do have another computer here from which perhaps I can... I do apologize very much. I'm so sorry for this.
No problem, no problem.
I'm using Teams regularly and couldn't anticipate that something like this would happen. Let me just try to connect through the other computer.
Okay.
Peter, if it is taking long, can we go ahead with the next presentation and then once Alexandra is...
I'm not sure if the next speaker is actually already here, to be honest.
I can always ask the next speaker if he can come early.
Let's.
If Jonathan is the next speaker.
Yeah, he is. Yeah, but let's see what's happening now with the new computer.
Yeah, sure.
Alexandra, you're muted actually. Good news, we see the screen. Yeah. The bad news is that we cannot hear you yet, but I guess if you unmute yourself, that should. Alexandra, are you talking now? We cannot hear you. Teams lists you as being muted.
Peter, you can normally also unmute as organizer.
I'm not really the organizers, but Kamal, can you unmute Alexandra?
Actually.
So we see the slides, but we still cannot hear you. Peter Jan, perhaps it's not such a bad idea to ask Jonathan if he could come earlier. Because it seems Alexandra cannot hear us either.
Yeah, I send him a message on WhatsApp.
Okay, thank you very much.
He hasn't read it yet.
Oh, I'm so sorry. I don't know what else could go wrong. Okay.
But now it seems to be okay. So we see you, we hear you, we see the slides. I think we're all set.
Okay, thank you.
Don't worry about it.
One sip of water.
Of course. Yeah.
Okay. So let me just put on full screen. I'm sorry, it doesn't, again, I cannot change the slides. Something is wrong. I'm sorry. It's just.
Is it an option to continue without full screen? I think it's more or less okay like this.
Okay.
Yeah.
Okay, so thank you again very much for this invitation, and I apologize again for the technical problems. So my talk is devoted to applications of AI in computer vision, and especially to challenges in high-dimensional and multimodal data analysis. Today, high-dimensional and multimodal data are being routinely acquired in various applications. For example, in remote sensing, hyperspectral images are often used, which contain even hundreds of spectral bands. And then this is another example case study that I would like to discuss today, is the application in digital painting analysis, where we are also typically working with multiple modalities of images. Let me just ask you, is my mouse visible on the screen?
Yeah, we can see the mouse.
Okay. So let me just changing the slide, doesn't work. I don't know. Oh, I'm sorry, but I cannot again change the slides. I don't know.
I think we should ask Mr. Murphy to leave the meeting.
Yes, yes. I don't know what to do.
Can I propose then, Alexandra, while you solve the problem, we can go ahead with the next speaker?
Yes, yes, please. I apologize so much for this. Yes, I will solve the problem. I do apologize very much.
No problem, don't worry about it.
Okay.
Yeah.
If you can't share, then we can share the screen.
Okay. I will then stop sharing.
So Peter Jan, could you still ask Jonathan to come now? Sorry for the ping pong.
Yeah, I asked again. He's coming.
Okay, great. Thank you very much.
Yep.
Hello, welcome. Thank you very much for being flexible with the timing here. We have some technical issues. So our next speaker is Jonathan Berthe from RoboVision. He's actually the founder and the CEO of that company. So a Belgian company that specializes in industrializing deep learning. He is, again, another graduate from Ghent University, and then he moved to do neuroscience at ETH Zurich. And actually in 2018, he was voted Disruptor of the Year, and he's also very interested in addressing societal challenges. So we're very interested to listen to your talk about industrializing deep learning. So the floor is yours.
Thank you so much, Peter. Hopefully I don't have PC problems. So let's see how that works out. I'm going to start my slideshow. Can everybody see me?
So far, so good.
Okay, let's click the button. So it works. Is it? Do you see the first slide?
Yeah, but not in presentation mode. Yeah, there it is. Yeah, it works.
Okay, great. So I'm Jonathan Berthe. I'm the founder of RoboVision, and I'm going to tell you a story how my passion of image processing evolved from coding myself in an algorithm creation-like way, starting with segmentation tasks and everything. I started with that, as was earlier mentioned by Peter, in 1999, the lab of Luc van Gool, very well known in the world of image processing in Zurich. And how that evolved into a frustration that you cannot just keep on coding algorithms for all complex problems out there, into a deep learning platform. And time was with me. I was very lucky to be an entrepreneur at a turning point in history when old school coding, Andrej Karpathy mentions it as software 1.0, became software 2.0. So I'm really happy to tell you that story. So if you look at where I started really duct taping solutions. As you can see here, the very first trial, I was always very much recording my stuff, even 15 years ago. This was 13 years ago. It was really the very first things I did. You see that this robot is making very funny movements. These were algorithms where I really had to hard code where to find the plant, and it worked somehow in the beginning. So I was very happy that Together with this shaking belt invention, which is patented right now, this evolved into what is now a deep learning platform with hundreds of deployments worldwide. So it's a story of a Flemish startup that became Scale Up of the Year 2020, and what caveats I had to manage and how we evolved into a team of nearly 100 people right now. So that is where we are now, a scalable deep learning platform where a lot of applications can be annotated, where there is a no-code flow going from annotation, and where we do projects such as the Nobi lamp, where we do pose detection for fall detection, where we also do traffic analysis system with AWV, security detection systems, and yeah, just more usual stuff. So RoboVision, we started with robotics and vision. My passion really lay in this combination, and I decided to go for a very straightforward name that explains everything. And we added, the symbol of a neural network some years ago when we went all out for this deep learning-based platform. This is a pre-Corona picture. Even in Corona times, I think we added some 35 people to the team list. So we're very centrally located in the Tech Valley, Ghent. And we see ourselves really not only as a platform company, but also as a team that is able to transform PhD knowledge into products. If you look at people working for RoboVision, there are quite some PhDs in our team that are very, very enthusiastic because finally they can work on real world problems with real world data sets and challenges that are often not seen in the context of a PhD thesis. So that's we're happy to do that. We also give already for the 4th year the lecture of AI of Alexandra Buzurica. We also give a Practica in the last year. So we see a healthy ecosystem. The Ghent ecosystem is a fantastic ecosystem for AI companies. A lot of good people, a lot of people that are very passionate, like Peter Jan here on the call, and that help us go to stellar heights. So we're with 4 different verticals, focused on 4 different verticals, all deep learning on visual data. And our challenge is, of course, to industrialize deep learning. That's the title of this talk. And industrialization is not just a fancy term. It means an awful lot if you go to the industry, because if you look at the second video feed, it's a machine planting plants. And if you deliver the machine to a farmer everywhere on earth, we're even in small town Japan, Insai City, Sydney, even in Canada, Leamington. So if you deliver a machine to such a farmer, the first thing he asks is, will you be there in 5 years? And what if something breaks in 5 years? And that's not only mechanically, that's also, of course, software. Because if your PC breaks and you have to buy a new one, then you're, of course, confronted with the fact that a lot of things might have changed, and support with drivers will not support your early CUDA version of 5 years ago. And the real challenge is that, a company called NVIDIA, that all of you know, of course, took over this hardware market in terms of deep learning. It's the one and only at the moment in the context of industrial deep learning. There are, of course, some others like Xilinx and Intel, but they don't mean a big thing in the AI community of hardware. That company was, of course, known as a gaming company. So they're very much into marketing and hype cycles and deliveries, generations of hardware that have a lifetime of not longer than 1 to 2 years. So it's really, really difficult to combine that with the concept of industrialization, because you just cannot buy hundreds of old GPUs just in case in 5 years you need to put them on a hardware, on a main board. So that's actually our challenge, and I will go through that. So it all started with, as I mentioned early on this talk, with coding ourselves, having dedicated algorithms in the industry and beyond. And this always had to do with human-made intelligence, I call it. intelligence that is engineered by a designer, by a software engineer, or just an applied physics engineer like me, that has to do with understanding the problem first. What is at stake? What do you need to measure? And then executing it in an if then else way. I mean, just coding, just software 1.0. And basically, for a long time, it was segmentation. A task of segmentation is, of course, subtracting the background from the foreground and having and detecting the essential stuff inside the foreground blobs. That was image processing for decades. Now, that's really difficult if you have very flexible realities like agriculture, where plants are of different breeds depending on the era in the year when they are grown. So at some point, we decided to go to deep learning, first to machine learning, when I actually contacted in 2012 the University of Ghent. Was a schoolmate of mine that I knew from when he was 9 years old, that had become a professor. It was Benjamin Schrauwe. He was working together with Joni Dambré on a lab called Reservoir Labs, and I was visiting the lab and I said, like, I have a real problem. I just cannot keep on writing algorithms. I don't have a scalable model. And they were always talking together with David Verstraeten and Tim Wageman about machine learning. It was one of the first time that I heard it back then, 2012 or earlier. And that's when I decided really to work together with them. And at some point, Ben advised me to work with some guy that was just ending his PhD. We decided to build his robot. And that's where we actually converted this model from writing our own algorithms into scalable algorithm creation. And in the end, it became deep learning. Deep learning with the very first networks. Of course, AlexNet was one of the first ones, but the very first networks that really worked well in the industry were the so-called UNet. So we decided to go all out with the UNet together with a thesis student. I think it was Wannes Bouwe, and also ID Lab. They changed name from Reservoir Lab to ID Lab. And this UNet was working really well. The only thing that we needed to do with this UNet was right kind of augmentation, because our farmers didn't want to label for thousands and thousands of images. Adding some tips and tricks that some of you know, dropouts, and making sure that we were not over-classifying or over-training, that you can see in the center bottom of the image. But there are some differences between academic deep learning and industrial deep learning, because in many cases, overtraining is actually a good thing in the industry. If you have a pedestrian detection system, and you overtrain it slightly into a specific context, like a specific crossroads, it doesn't matter if you just spent 1 day to label extra for this crossroad, but if it's overtrained, it will just work much better on that crossroad. It doesn't matter that you cannot write a paper about it, that it's just not really well done from a deep learning perspective. But these kind of things are really important to note when you decide to industrialize deep learning. And maybe some of you don't know the concept of neural networks, just a very dummy slide this, but of course it's all about generic architectures like semantic segmentation. I think mask-R CNN is something we have very often used, and just adding a lot of imagery to this bottom layer in this case, the pixels connecting them to the neurons or the input layer of the neural net, and then regressing this connection with, of course, gradient descent and similar methods, until you get a situation where the right connections have been formed, and that you have on the image batch at stake regress those connections into a performance classification algorithm, in this case cat or dog. But if you want to industrialize deep learning, of course, it's important to note that we've faced like a Cambrian explosion in the last years. Everything was quite stable when the Canadians were actually, together with Geoffrey Hinton, Joshua Benju, were pioneering. It was all Theano, And actually, the University of Ghent was relevant in this pioneering phase, because the package made by, I think, Sander Dieleman of Reservoir Lab, Lasagna, was actually the philosophy which was applied by TensorFlow, the kind of script that you could create without writing a lot of code to define your deep neural net. Because Theano in itself was basically a mathematical library that leveraged the use of the GPU. So if you look at all these packages that emerged in the last year, it is like, yeah, it's like football. You have Manchester versus some other football team. You have the PyTorch guys versus the TensorFlow guys. And the problem is they all solve some stuff. PyTorch is really good at multi-GPU. It makes it easy with the Lightning package. And Keras is, for instance, really interesting for beginners or for people that want to get started really quickly. So we, as a platform, because we sell a platform, we have to make our technology available to integrators. We want to abstract this away. We want to abstract the concept of a neural net library away. And that's what we do with the concept of cells. Cells are basically, because we adhere to the Docker Kubernetes principle of abstraction, scalable, good practice in the cloud environment nowadays, we abstract the concept of the framework away inside a cell. And this cell is actually the atomic unit of intelligence. And it's with these cells that we create actually deep learning. Some other fact about deep learning, the so-called Cohonen feedback network or backpropagation network is very old already. And it's only in the 90s that people realized that when they wanted to get scalable algorithms or scalable neural networks better, that to connect all these networks together between the different layers was just impossible. And it actually coincided with a time, the 90s, where there was even more brain research. And what was actually clear, I was a student, of course, at the time, not a PhD. I never did a PhD. But in 1999, these experiments on cats in, for instance, ETH Zurich, really led to the fact that people really started believing in nonlinear kernels. It was, of course, the time when wavelets came up, and Fourier transforms were actually seen as not an optimal way to compress imagery or analyze imagery because of the black and white boundaries that are, of course, similar to delta functions containing too many frequencies. And with these insights in neuroscience, the ganglion basal cells that do this Mexican hat-like filtering, converting optical, basically photons into biochemical signals, it was actually, this coincided with the time that people like Jeffrey Hinton and Joshua Benju were designing these networks in a much more efficient way, so-called convolutional neural networks that were basically automated kernel tweakers, where actually the kernels that are formed in these intermediate layers, the kernels that you, for instance, see this kind of filters in the middle range of imagery, are formed automatically. And that leads to a very genius thing, that you, as a software writer, do not need to look for filters yourself. When I started writing image processing code, I basically had to know all these filters, Canny, Edge, Harris, corner detect, you name it, Gaussian filtering, Laplacians to have the edge information of an image. You had to know this complete library and to know where to pick what kernel to have efficiency and performance in your algorithm. And that really changed. With the advent of deep learning, we received an algorithm factory that did it for us. And it was with the advent of ImageNet, Fei-Fei Li, that actually this competition gained popularity year after year. It became like an epicenter for this new technology with the NIPS conferences, and where people were interchanging new kind of architectures. And it really led to things that you can see here, really efficient segmentation of everyday reality. And if you look at how to industrialize that, if you want to abstract the coding away from the workflows of the operational people in greenhouses in this case, or in companies that make things and need to do quality control, then it all boils down to data curation. So algorithm development has evolved into data curation, data labeling, and in such a way has created a more ease of use to generate an algorithm. And of course, if you want to industrialize that, if you want to make it available to all of these institutes, companies, small and big, then you need to build a platform around it. And that's what we started doing in around 2014. It was first really naive with some only one network and some click and play, but it worked. I mean, we sold like first hundreds of machines, and afterwards it just kept on growing. So in the end, if you look at the complete pipelines that we do, it is actually data curation, and the core value proposition that we bring to the market is bringing this expertise, democratizing this expertise and bringing it to the edge. It's an industrial term, the edge, but it means the machine. It means that the farmer, when his connection dies down because he's in the jungle, we have machines in the jungle, that the farmer, I'm going to close the door for a moment because they're ping-ponging right now. 1 second. These farmers, when their connection is not there, and it, of course, in Europe, we're very well, how could I say, connected. We take the fiber for granted, but in large portions of the world, that is absolutely not the case. So you need some kind of platform on the edge that also can just work when there is no connection. And that's our value prop. And we have seen that this value prop in semicon is actually very relevant, because if you want to develop the Apple M1 processor, there is so much industrial espionage that you're even not allowed with a USB stick inside. So the complete platform has to run in the cabinet just near to the electron microscope, as is in the case with our customers. So we were happy that this attitude of industrializing deep learning with a platform on the edge for agriculture also paid off in making nice deals with the biggest semicon companies in the world. So if you look at the ecosystem, it is maturing. It is maturing in the sense that some years ago, you had companies like Johnson & Johnson, UCB, other big corporates that just were nervous about this new wave of AI and just told their HR teams to just hire AI experts. So what they did is they hired mostly PhD people, because you didn't have this deep learning programs at university some years ago. And they arrived in big companies, and they were confronted with ecosystems that were not compatible with deep learning. Citrix, Windows Active Directory like stuff. So everybody was like getting a gaming PC or some PC where this fast GPUs fitted into, and working on his own notebooks, until the management of these large corporates realized that it was no longer manageable. And then, of course, people started thinking about team collaboration, the same way that code development evolved from sending zip files to each other in the 90s until the GitHub phenomenon, GitHub at the moment. So what we see is that if you want to let people work together, you have to reuse existing building blocks. Otherwise, you're just exchanging notebooks, and that leads to a lot of chaos. And you need easy integration of different machine learning technologies and frameworks. As I told you earlier, the concept of a cell, where a cell can be put into concatenation with other cells and lead to a pipeline where also your inference can actually fastly run on. So it's yeah, the concept of building pipelines and also at inference time, making sure that these pipelines are just working really efficiently. And that led us to another problem, because it's one thing to train a network, but it's another thing to run it at a scalable way. I'm at this moment in Amsterdam, near a ping pong table, but here we are actually building a computer of 190 megawatts with 10,000s of NVIDIA GPUs. And to run algorithms on such an environment, you just need dedicated frameworks to leverage on that. And if you look at the problem at stake, for instance, smart cities, you have a data stream, you have object detection, and in this whole train of events, you need to pass information from one model to another. But of course, when you're doing so, you have your object detector that takes, for instance, 50 milliseconds. You have your tracker that takes 60 milliseconds. And then you do some consecutive operations like anomaly detection or speed, and in the end, visualization. So if you add everything up, you slow down your train because it's not working in parallel. So you need to think about parallel frameworks. But of course, parallelisms and Pythons, they live on some kind of tension, of course. So we decided to go for Ray, thanks to Robert and Peter Jan, our Ray hackers. I know Peter Jan is on the call, but Robert, I'm not sure. And then we could just leave it to a Ray environment, to actually a distributed compute environment that abstracted away the fact that you have a lot of different actors, Ray actors, that are being used and being organized in such a way to have efficient workload handling. You parallelize your machine learning workloads. And the RoboVision platform is built on Ray. Ray is from a company called Anyscale. Ian and Robert are the founders. We know them well. We have already a lot of C-level contacts with them. And I think Peter Jan is on a weekly basis thinking with them, because we are really their use case providers. So we are pioneering in this field of industrializing, but also scaling up AI operations. So in the end, concluding our cell-like architectures, you have all these different cells like spot cell, classify cell, and you can put them into pipelines. But that's not the only thing. Of course, you need scalable tooling for data curation, meaning you need labeling tools. You need tools that are that can be used to label a lot of different contexts, from cars to pigs, from pigs to lungs. We worked on the COVID-19 track together with the National Cancer Institute in the Netherlands. And for all of this tooling, you need ways to distribute them to a lot of annotators. So the best way to do that is, of course, to work in a web-based environment, because you know with web-based environments that they are most democratic environments, meaning not depending on the specific hardware architecture. And of course, we also needed in agriculture to build 3D-like tooling, AutoCAD-like ways to annotate 3D morphology in order to use these different 3D-like deep learning, for instance, in this case of the COVID detection, and to use scalable annotation in conjunction with 3D architectures. And as a partner or as an institute, university, you can just create no-code workflows, easy wizards where you can go from data annotation to thing. And our belief for the ecosystem is that in the future, what we will see is AI exchanges where universities and companies can just put models or pipelines and can be trained, and you can just much more easily connect capacity and opportunity. Imagine that the deliverable of a PhD thesis is not only a booklet or a PDF on archive, but also a model in an AI exchange. It would also mean more easy creation of startups and scale-ups, of course. So our applications, we became a scale-up due to our success in horticulture and agriculture, and that's because we made things really easy. As I explained already, just labeling on the edge, as you can see here. Just put your plants on a blue conveyor belt, draw arrows where robots shall pick up those plants. The arrow, of course, the direction where the plants shall be oriented with regard to the soil. And after 15 minutes, because of all these tricks I mentioned before, and the transfer learning aspects of the network, you could just start planting plants. Whole variety of plants. I think Florensis, which was posted on our LinkedIn some days ago, has in total like 1,200 models created by non-IT people, which is quite impressive, of course. And of course, you get then the concept of robo farms, where people are only just emptying bags and all the rest is done by robots just being trained with neural networks. As said earlier, also 3D deep learning is something we've been working on in the last years, and we've been creating machine after machine to be able to understand reality better with the help of deep learning. We'll skip this for a moment because I see I'm near the deadline of my speech. A machine that we're particularly proud of is that of the automated rose pruner, because it's also the base technology of a market that we plan to conquest in the next 18 months, is that of automated harvesting robotics. So what you see here is labeling of a rose in order to make sure that this rose is actually cut in the right format. Right format in the sense that every cutling just need one side branch for the photosynthesis to kick off, of course. And if you put it into context of the RoboVision platform, our PhDers have created an automated workflow here, a 6-step process where you can go from data onboarding, all in cloud normative ways, S3, and where you can just give access to the right labeling pool, create your classes in a click environment, and in so making it easy for an operator near the rose cutting machine to actually learn a new rose type, because of not all roses are created equal. Other very important machines for the next years that we're actually also distributing right now is the plant sorting machine, a machine extremely relevant for seed enhancement. The companies like Rijkswaan, Bayer, BASF, Enza seeds, all customers of RoboVision, where you can, if you have a genetic manipulation of your DNA string, have more easy evaluation what it does with, for instance, the leaf content or with the aspects of the plants. And then you get a kind of 3D analysis of the complete plant, of course. Another way of scalable AI is retail, where we installed and tested out deep learning systems in the supermarket of Colruyt. Scalable AI in smart cities. It is something which will gain enormous importance in the years to come. Of course, when you track each car individually, it's much more easy to predict problems in traffic flows. We also work together with the Flemish government to make corona scanners. It was before yesterday in the news. The Mer, the most busy shopping street in Belgium, was actually used as a detection site for RoboVision software. Anti-terror systems in the station of Utrecht. Then we also have other kinds of tunnel anomaly detection systems where pedestrians are detected, and healthcare. So the Nobi lamp was actually co-created with a company called Nobi. We kickstarted them with our deep learning models, and they won a CES award 2 weeks ago, also Hanni van der Velde award. So what we see there is that if you create rapid workflows of deep learning annotation, you get a much more easy product development, as we can see with this beautiful lamp that prevents people from lying on the ground after they've fallen in an elderly flat, for instance. And that is about it. I have 32 minutes to conclude. Actually, scaling AI is a challenge. You cannot just map the academic ecosystem onto the industrial world and hope it will work. We see a lot of tensions. We see a lot of proof of concept not succeeding because of mistakes that have to do with the chaotic ecosystem in AI right now. And I'm happy that I could tell you the story of RoboVision. Peter, the word is back to you.
Thank you very much. Cool stuff that you've presented. Very nice. While we're waiting for the chat to ask some questions, I have a question myself, more philosophically, societally speaking. So it's clear that deep learning will take over many jobs from many typically lower schooled people. So what do you think is the best way as a society to deal with these kind of issues?
Oh, it is to educate people about the caveats of deep learning in the sense that automated algorithm creation also brings us a new problem. That is that we don't exactly know what's in the algorithm, of course. One of the reasons I pushed away neural networks in the first year of my career, because they were there already, was that I was always explaining, yeah, but if the neural network is trained, you don't know why it failed at some point. And I think academia is doing a good job in actually make more explainable AI. But I do think that our society of tomorrow must be a much more meten is weten-like society, a society where measuring reality will lead to more accountability. I think the future Ministry of Transport or Traffic in a good working nation state must act on information. It must be a gigantic cost function to have a most efficient traffic network possible, and all the rest is just periphery. I think people are too central sometimes in things that where automated technology can do a lot more stuff. Okay. Emmanuel has a very long question in chat about the case of overfitting with the traffic light. But perhaps, Emmanuel, it's best if you unmute yourself and ask the question directly.
Yes. So I wondered, you talked about how overtraining can sometimes be advantageous in an industrial setting. And by that, I guess you mean that it can be beneficial to focus on particular critical cases, even if it comes at the cost of the performance in more general cases. But is this not a symptom of just needing to diversify your machine learning models? For instance, using a different machine learning model for the critical cases than for the cases in general?
Yeah, that's a very good question, and I think you're right in some cases. If you apply that to the plant industry, it's what we exactly do. We just build different models for plants that are slightly different. In the case of traffic situations, we have to be really careful because a different plant has a different name and has a different engineer who made that plant or engineered that plant. If you go into a traffic environment, it would be really chaotic to have Mortsel Oude God crossing in winter snow times, and that you had to detect snow first to apply then the snow trained network. So we try to prevent like a Cambrian explosion of models in the smart city environment and only work with dedicated overtrainings on sites, but not with different models on site, because then it really becomes like a management hell.
Yeah, that's an interesting point, yes. So yeah, having more general AI that is overtrained on certain cases is beneficial in that case. Thank you for this insight.
Okay, thank you for your question.
And then a final question, could you elaborate more on the difference between software 1.0 and 2.0?
Yes, it's a very good question. I think we, as engineers and technical people, we've all been schooled with the so-called von Neumann model of the compute architecture, the CPU, the memory paradigm, where a program is a set of instructions that is sequentially read into the processor together with data to deliver some result. And that requires some engineering of building this kind of decision tree, this kind of sequence of things. And hence we have all these compilers, of course, that come up with abstractions to make it less difficult to create this machine code. But This is what I really call 1.0. It is this paradigm of almost sequential tasks where you first do the general segmentation and then go up to the more details of your problem, process your blobs, for instance. And this is in sheer contrast with software 2.0, where the whole concept of if-then-else clauses becomes completely irrelevant. You are just adding the right created data to something generic, which can be the same, exactly the same architecture in healthcare, agriculture, or in smart cities. And it's really sometimes shocking to explain to our customers and other people that are interested in the story of RoboVision that we use sometimes exactly the same deep architectures in different ecosystems, and that it all boils down to data curation. That is what we call software 2.0, a heavyweight component on data curation instead of manual engineering of the algorithm, and hence more alignment with how we think as biological entities, because this second approach is much more intuitive. It is just like people that have never heard of software of IT, they will just work with examples. It looks like this, and can you give another example? That's how we learn. We do not actively think about if then else when coping with reality.
Okay, thank you very much. Let's now take a 10-minute break and we'll reconvene at 10 to 5. And perhaps, Alexandra, we can set up the presentation and check it.
Okay, thank you very much for having me. And yeah, I'm really happy that I could tell the story. I absolutely have no clue what kind of audience is here, but just quickly browsing to it, I think it's a bit 50-50 in terms of external versus internal people. I don't know. What do you think?
That seems to be the case. Yeah, I think it's a very mixed audience. There was a great people in the chat comment that they like it a lot, so that was really great.
Yeah. Okay. Super. Am I expected to stay here or?
Not really, no. So feel free to address other commitments. No problem. Yeah. And thanks for being flexible to come early.
Yeah, I was actually still building my presentation, and that's why I at some point had to go back in slides.
Yeah.
Please follow us on LinkedIn if you liked it. On LinkedIn if you liked it. I will just add a RoboVision link here. So Peter, thank you so much. And if anybody wants to contact us with some inquiry or something, the best way to contact us is via info@robovision.eu.
Okay, fantastic.
Enjoy your weekend.
Okay, thank you. Bye. Likewise.
Bye.
Alexandra, are you there?
Yes, I'm here.
Yeah, perhaps we can try.
Yes, I think it should work now.
Okay, great.
There was some problem with the privacy settings, but let me now start. Do you see the presentation now?
Yeah, it looks perfect. Yeah.
Okay. I'm so sorry for this again.
No
really,
problem.
I mean, you
Yeah.
wouldn't believe, because actually it was our system administrator made some updates to the computer, and because it is a Mac, there was something with privacy issues for Teams. It had to be enabled for screen recording, and he didn't do that, and I didn't remember that it had to be done. So I'm so sorry, really.
No problem. It happens to all of us. Yeah, we certainly sympathize. Yeah. Okay, great. So then we'll start in a couple of minutes, 10 to 5.
Okay, see you then. Okay, bye.
Bye. Okay, welcome back, everybody. Let's continue. Alexandra, floor is yours.
Hello. So let me share the screen. Can you see the screen well?
Yes, it's perfect.
Okay. Okay, so thank you again for this invitation to participate in this nice event. My talk will be devoted to applications of AI in computer vision. And so especially I will talk about processing high-dimensional and multimodal data. And these are today being routinely acquired in various applications. I will use as case study two, actually, and one is hyperspectral imaging, and mainly I will show examples from remote sensing. And then the other application that I will devote some time to is analysis of digitized paintings. And this is interesting also because here we are dealing typically with very huge images acquired in very high resolution, and we also have various modalities like infrared, X-ray, visible, and so on, and then with all the problems that are connected to, let's say, extracting information from these various modalities that are not perfectly aligned, that carry different information, and so on. Let me start first from hyperspectral imaging. Hyperspectral imaging is very important across various applications because it provides, let's say, very fine spectral information which allows to distinguish between materials which are otherwise non-distinguishable just in the visual domain. Now, in various applications, hyperspectral images are being used. I will give examples from remote sensing. And in remote sensing, often you have these images containing of several hundreds of spectral bands. This image here is an illustration that comes with a special type of spectrometer, which is HyperScout, the first miniature hyperspectral imager for space. And why are these interesting? Well, this type of sensors are very important also in environmental monitoring. In fact, it has been also recently, let's say, they have been recently referred to as game changer in environmental monitoring. For example, DLR's Earth Sensing Spectrometer is installed on the International Space Station, where it monitors environmental changes on Earth. What is interesting to observe is the size of these imagers and of these mini satellites that carry them. So often these spectrometers are embedded into miniature satellites called CubeSat, and the size of which is 10 by 10 by 10 centimeters. So you can see here they can fit, you can hold them in your hand. And then, of course, it means that the processing power and memory and energy actually is very limited, and it means that we need to devise clever algorithms that are able to process this huge amount of data that is being acquired in an efficient way. And then the other application that I mentioned, so in analysis of digitized paintings, what you see here are some examples that are actually from the Ghent altarpiece. Peter has mentioned at the beginning Ghent altarpiece, so I will come back near the end of the talk to show also what we did in this domain. But let me now first start from some, let's say, generic concept which underlines many of the things, let's say, that I will be talking about today, and also aspects that we have heard about in the talks previously. And this is sparse representation. So when we say sparse representation, we mean that an input sample, and this input sample can be a spectral line taken from such a hyperspectral image, or a small patch from an image, or any other input sample. So it is sparsely represented if it is represented as a linear combination of relatively few elements from a given dictionary that is represented here by D. Now, if we say sparse representation and dictionaries, it is difficult actually to skip wavelets. So wavelets have made a revolution in their time in signal and image processing. They are carefully designed dictionaries which allow very sparse representation of signals and images. So here we see a wavelet representation of this input image, and what is shown is this typical representation where we see magnitudes of the wavelet coefficients in different resolution scales and in different orientations, and then only those that are of large magnitude are visible here. So the magnitude is proportional to the brightness, let's say, in this representation here. And then you can see that most of these coefficients are actually zero or nearly zero. But over the years, improved versions of wavelet representation have been proposed, wavelet-like representations, which offer even better orientation selectivity, even sparser representation. And these are known as curvelets, shearlets, contourlets, and many others. And then even further on, a further improvement was made by switching to learned dictionaries. So where we are actually not designing the dictionary in an analytical way in advance, but we are learning this dictionary on some set of representative training examples. And in this way, we can obtain optimally sparse representation for a given class of signals. Now, the sparse coding problem is illustrated here. This talk will not be a mathematical talk. This is one of the relatively few equations that I will show. But I think this one is important because underlines a lot of other developments. So once we have a dictionary constructed in a given way or learned, then the basic problem that we need to solve is to actually calculate these coefficients that determine the optimally sparse representation in this dictionary. And this problem is called sparse coding. So it means actually we want to minimize representation error, requiring that only relatively few, so some k of these coefficients are non-zero. Or we can formulate this also alternatively, saying we minimize the number of non-zero coefficients, requiring that this representation error is below a certain threshold. Now, this problem is NP-hard. And so it is typically solved by greedy algorithms such as celebrated matching pursuit, orthogonal matching pursuit, iterative hard thresholding. And there has been a huge activity in the field on developing these various types of algorithms. But what is also often or even more often done in this context is to apply a given convex relaxation, which means in this case replacing this L0 pseudonorm by L1 norm, so actually requiring that the sum of the absolute values of these coefficients is below a certain level. And then this problem is actually solvable by linear programming methods. It is often referred to as lasso problem or basis pursuit denoising. Now, this was all considering that we already have a constructed dictionary and that we need to determine only our coefficients. What we have most of the time in practice is actually that we don't know the dictionary and we don't know the coefficients. So we have to learn both simultaneously. And then this is done by actually inputting a number of these input samples, like these spectral lines or little patches from an image or whatever is relevant to our problem. And then we formulate an extended, let's say, variant of this problem where we are simultaneously actually learning the dictionary and the coefficients. This problem then is solved in two steps. by alternating between sparse coding and dictionary update. What does it mean? We will first start from some initial dictionary, which can be a random dictionary, or if we are talking about computer vision, this is typically a DCT or alike dictionary. And then we solve the sparse coding problem, then we update the dictionary and again solve the sparse coding problem. And in this way, alternating between these two steps, we are actually solving this problem. Now, there are various methods of this kind, and they basically differ in the dictionary update step. The best known is probably KSVD algorithm, which is mostly used in computer vision. And here you see examples of dictionaries learned by the method of Olshausen and Field, which was the first. It was a seminal work, actually, in the first dictionary learning method of this kind. And the dictionary learned by a KSVD algorithm. Well, we have seen in the talks today already actually how these various dictionaries of so image atoms are connected to deep learning. And so it means actually if you have learned a good dictionary, then for any other image, if you are talking about images here, which shares certain properties with your training set, then you will be able to represent every small patch from such an image as a linear combination of relatively few, let's say 3 to 5 elements of such a dictionary. And then we can apply this process also at different levels of abstraction, and we can create multi-level dictionaries or multi-scale dictionaries. So I guess at this point, many of you will see the direct connection with what you obtain, let's say, in learned features in deep learning. And indeed, this is the case because this is also a general, let's say, approach to representation learning, where you can also formulate dictionaries learned by convolutional neural networks or by these other more, let's say, rigid mathematical approaches. But they do share a lot of in common. And I must say, although convolutional neural networks are being successful to learn more flexible representations, on the other hand, sparse coding has the advantage of explainability because it is formulated in a rigorous mathematical way. And now that there is more and more interest in explainable deep learning, there is also a lot of interest in actually explaining convolutional neural networks via convolutional sparse coding. I will not talk about this further on, but I find this interesting. Now, let me also mention just very briefly this representation, which is called sparse representation classification, which is very interesting across various applications. It has been used with huge success because there we are actually don't have to learn this dictionary, but we are constructing it by taking samples from given classes. Let's say if this is our input, let's say hyperspectral image in this case, and suppose you have some labeled samples for classes like vegetation, waters, or urban areas, and then you can construct based on those samples your structured dictionary, and all that you need to do is to solve the sparse coding problem and then finding which of these sub-dictionaries gives you the smallest representation error, and then you can assign your sample to that class. Well, in practice, there are, of course, various other practical aspects, but in a nutshell, this is a basic idea, and this approach has been actually hugely popular also in remote sensing. So this is also where we did a lot of research, and one aspect there that we were interested in was to introduce sparse noise, how to make these methods more robust in the case where you have some noise, some dead lines, various types of impulse noise that typically occur in this type of images. And then, okay, we can formulate the optimization problem, and these problems are typically solved by using methods called ADMM, alternating direction method of multipliers. Now these are some examples of then how this is if you apply such a method for the classification of hyperspectral images. So this is typically a representation that we show in this domain here. Well, the black areas here are shown because these are the areas where we didn't have some information about ground truth labeling. So this is typically represented in this way. Now, another interesting problem, which is closely related, let's say, if we look formally to the description of dictionary learning, is the problem of unmixing. If you take hyperspectral images, these images have fantastic spectral resolution, which allows us to distinguish between materials that are otherwise visually undistinguishable. But on the other hand, there is a trade-off between spatial and spectral resolution. And that typically, sometimes, let's say in satellite hyperspectral images, the pixel size is 30 by 30 meters, sometimes 10 by 10 or 1 meter. But in any case, you will have some mixed materials within 1 pixel. And it is of importance to develop algorithms which are able to determine in which proportion various materials are present in a given pixel. This is solved with the same actually type of methods that I described by sparse coding, because what we had as a dictionary there is actually given in this application as a spectral library. And what we solve as sparse coefficients are actually the abundance coefficients. We have also worked on this problem. This is an example of applying sparse unmixing in remote sensing, determining different proportions of different materials in a given pixel. But basically, this problem is very interesting in many other applications. Let's say if you take paintings, it is also of interest to determine the fraction of various pigments. And also one very nice application is in medical domain, where let's say in analysis of skin lesions for determining, let's say, the probability of skin cancer. This is some emerging area where multispectral and hyperspectral sensors are being increasingly used, and then using sparse mixing is actually crucial there. Now, yet another, let's say, problem when we are working, when we are talking about the analysis of high-dimensional data is clustering. So in many applications, or in many cases, we do not have labeled data. And when we don't have labeled data, we still want to be able to somehow determine to cluster, let's say, pixels in this case, which share certain properties. And then this type of unsupervised classification is also called clustering. So here I want to, let's say, just draw your attention to this approach of sparse subspace clustering. This is, I think, really a beautiful mathematical idea, in fact, which, let's say, has resulted in has inspired a huge amount of research. And this builds on the sparse coding model that I introduced at the beginning. But what is special here is to say, okay, we have our input data, which is represented by this matrix. And these colorful squares are there just to illustrate that these are some arbitrary real numbers. And then we use this same input matrix as the dictionary. And then we solve the sparse coding problem. Now it can appear weird, why would you use the input data as the dictionary? But in fact, this is a very nice idea because we will introduce some additional constraints to prevent that this sparse coefficient matrix is just diagonal matrix, so to prevent a trivial solution. And then what we obtain when we solve the sparse coding problem, we just actually obtain from our coefficients the information about which entries belong to the same subspace. Let me explain this like this. Suppose this is one input sample from this input matrix. Let's say this is one spectral line from this input hyperspectral image. And suppose when we solved our sparse coding problem, we got for in this column here, these two coefficients are non-zero, let's say the 5th and the 7th. This means then that actually our input coefficient y is well represented as a linear combination of y5 and y7, which means that these three together belong to the same subspace. So directly using this property, we obtain clustering. And so this is the idea on which we built also in our research on various levels, also introducing spatial information, making these algorithms more efficient. And this is one then example of how we actually apply this clustering so to a given hyperspectral image. This is all very nice in theory, but as it often comes in practice, we face some huge computational and memory problems. Well, maybe this is something that in connection with using photonics research may not be such a big bottleneck in the future, but in any case, applying these algorithms on standard computing architectures is, let's say, limiting the size of the images that we can process very severely. And then there is another, let's say, beautiful mathematical idea again, where you can apply some well-designed random dictionary, and in this way, actually, reducing the size of the optimization problem enormously. And this is a recent, let's say, idea, and the approach is called sketch subspace clustering. And this is something that has been since adopted, let's say, since a few years ago, also in various computer vision applications, but also in remote sensing. So actually, we were the first to build an algorithm for hyperspectral images based on this idea. And then, of course, we needed to solve some additional problems, especially taking into account spatial structure and so on. And in this way, actually, we are able to cluster very large-scale data. And you can see an example shown here. So for a given input image, these are various clustering results that you obtain by standard k-means. By traditional subspace sparse clustering, we were not able to process, simply the computing power was not sufficient and the memory was not sufficient, and then the results using sketching and this improved sketching approach. Now I would like to turn to deep learning aspects. So deep learning has also let's say, entered various areas of computer vision, of course, and many of the, let's say, developments have in fact originated and have been powered by computer vision problems. And also in remote sensing, this is also an example of a recent special issue devoted to deep learning in hyperspectral imaging. We have heard in the previous talks today and about neural networks and convolutional neural networks, which have been the dominant, let's say, deep learning model in computer vision, especially because of using these shared weights and making use of the non-local structure to reduce the number of connections. So this model has been hugely popular in computer vision. And so here is an example you have already seen in the previous talks. So convolutional neural network implemented as an, let's say, alternation of computing these feature maps by convolution and pooling layers, and then at the end, typically fully connected layer with the softmax rule, which gives scores or in terms of the probabilities that a given well, input corresponds to these given classes. Now, if you want to apply such convolutional neural networks to data like hyperspectral imaging, then the question is, how can we do that? Because, okay, we have 3D data and typically of huge size. Well, there are various approaches. Sometimes people apply even 1D CNN, because when you deal with hyperspectral images, then spectral information is the most discriminative one. So often only 1D CNN is applied. Or three-dimensional CNN, which is just extension of the classical 2D architecture to 3D, but this is not so easy. I mean, it is easy to design the model, but you end up with a huge amount of parameters. And Yoni explained beautifully in her plenary talk today these problems with overfitting and how if you have more parameters, you have more problems with overfitting. And so for this reason, it is also common in these applications to look to some other, let's say, approaches rather than just in a brute force extend the architecture as you have it, just to adding multiple dimensions. And then we have also various 2D plus CNN architectures. This is also the area where we did a lot of research in our group. So what was actually the focus of our research? Well, it was actually on two aspects. One of them was how to construct these architectures such that you can deal with relatively few labeled data without suffering from overfitting. And the other one is how to make these calculations feasible. And then, so we ended up here with various, let's say, models. Typically, we apply a combination of 2D and 1D streams for extracting spectral and spatial information. But also what is interesting is that you can apply fully 2D convolutional neural network and perfectly well process your 3D hyperspectral data cube without a loss of information. Well, this is what is often done first by applying certain dimensionality reduction at the beginning, like PCA. But you don't have to actually apply dimensionality reduction. And this has been also one aspect of our research. And trying to make these architectures such that you need to have less parameters led us also to the concept of group convolutions, which is let's say a relatively recent concept, and many computer vision architectures make use of group convolution. What does it mean? Actually, performing your convolutions between the groups of channels. but then in this way, there is certain, let's say, problem that you can neglect some very important correlations that exist among various channels. And then this is solved by introducing shuffling. And so this is, let's say, one aspect where we did also a lot of recent work. Also extending these models to fully group convolutional architectures, so where you are applying such, let's say, group convolutions in all stages of the processing and having some unified mathematical formalism which allows you to also make some elegant end-to-end learning. I will just go very briefly through these various, just to illustrate some basic concepts. So one important concept here was multi-kernel depthwise convolution, so which has multiple outputs for each of these inputs, and that we use actually to extract information at multiple scales in each spectral band. And then we have here a certain, let's say, shuffling of these channels. There is also, this is a technical term, squeeze and excitation. For people who are in this domain, they will know, but it's not so important to actually stress this, but it is practically interesting because then you can assign different weights to different channels based on their importance. And then in various stages, we apply actually these shuffled group convolutions. Also, residual learning is something that we found important to use. And what was also specific to this architecture that we developed is that also feature fusion step is let's say, realized as this sequence of actually shuffled group convolutions. So here you have a sequence of convolutions, permutations, and so on. Now, in the remaining part of my talk, I would like to just go briefly over the applications in digital painting analysis. But if I'm already over time, please let me know.
Yes, you are.
You're a little bit over time.
Okay,
afraid, yeah.
so maybe I can stop here, or I can give in 2 minutes.
I suggest a 2-minute overview is fine. Yeah.
Okay, I don't need more. So we did a lot of work in analysis of digitized paintings, and with recent restoration of the Ghent altarpiece, which attracted a lot of attention worldwide. And there were a lot of spectacular findings. For example, that nearly 70% of the painting was overpainted. So when the restorers removed this overpaint, some beautiful, even more beautiful original Van Eyck features appeared underneath, and the, let's say, biggest surprise was actually the face of the lamp in the central panel. So in this application, we work with multiple imaging modalities, like these ones illustrated here. And we tried to help the restorers in different way, detecting overpaint, detecting cracks. If you talk about crack detection, this is a very difficult problem in paintings. Like if you compare crack detection, let's say in road surfaces, then you have some uniform background. But on paintings, cracks can interfere with your painted structures, and it is very difficult to, and they change in the appearance from bright to dark and vice versa. So we developed some convolutional neural network for this problem, and we applied it to different, actually in different scenarios, but this is only one that I wanted to highlight here, of which we are particularly proud. And this is the following. During the restoration treatment, they needed to make a decision whether to remove the reinforcements that were placed on the back on the central panel. And the borders of those reinforcements are shown here in red. And then the restorers working on the problem, our collaborators, gave us the enlarged images and asked us, can you detect cracks in these areas around reinforcements? Because we would like to see if there is some increased crack density around these corners, which might indicate that, well, some mechanical tension was going on. And so then we got some scarce annotations. And so these are examples of crack detection run on these panels. And here is an enlarged part where you see the detected crack map in one of these regions. And indeed, there is some slightly, let's say, increased crack density around these sharp corners. So this result was also shown in the, let's say, expert group deliberating on the conservation of the Ghent altarpiece. And the reinforcements were removed. It's not because of our result, and they had their other means, but in any case, we were very proud that our result was also used as another, let's say, objective result in this whole process. And basically this brings me then to the end of this talk. Once we detect these various degradations, we also want to virtually restore these images. And I just want to mention, because icing model was mentioned in the previous talks, and so this is, we are working a lot in this domain with Markov random field models and among others icing model. And these are, let's say, inference methods, in this case based on belief propagation, and combining this with photonics calculations could be very, very interesting. And so I will just mention here, these are people from my research group, PhD students. Some of these results are from their PhDs. And also let me mention collaborators in art investigation. And especially I would like to mention Ingrid Dubishi, because we mentioned wavelets, not only me, but wavelets and sparse representations were mentioned several times. Well, Ingrid, next to, well, taking huge credit or for the development of wavelets, her great passion is also digital painting analysis. And I was fortunate actually to collaborate with her in this domain, and she was a great source of inspiration. And a little bit of advertisement, we have two special issues regarding to hyperspectral processing and processing of let's say in remote sensing in various aspects. So if some of you are interested, please feel free to contact me and to submit. By this, I want to thank you for your attention.
Okay, thank you very much for this nice talk. There's a couple of questions in chat, but I suggest in view of time that they also get answered through chat. There's one remaining speaker present, which actually happens to be me. Do not worry, I will not take the full 30 minutes for my talk. If you could stop sharing your screen, please, yes. Then I can, hopefully that works fine here. So the bad news is that I also do not see the window I want to share. Okay, give me a second.
Peter, I find Zoom so much easier.
Yeah, I've also had other issues with Zoom. I think it's always a problem. But let me now try and share my complete screen. That'll be better, hopefully. Okay. Do you see anything happening?
Yes, we see your screen.
Okay, great. So I would like to talk about a machine learning paradigm that we've implemented in Silicon Photonics hardware. And the machine learning paradigm is called reservoir computing. Now, what is reservoir computing actually? So in view of time, let me skip a few slides here. So reservoir computing, the essence of reservoir computing is that you actually have a photonic, or a neural network that's called the reservoir here in yellow. And it's very different compared to the deep learning neural networks that were discussed a lot this afternoon, in the sense that it's a recurrent neural network. So there are all these feedback connections there. So these things are typically very difficult to train. So what's done in reservoir computing is that these networks are just randomly initialized. So you do not train them at all. The only thing that you do train is this linear layer afterwards. So it's just a linear combination of certain signals that you optimize in order to perform a useful function, be it like speech recognition or time series prediction or something like that. So the essence of reservoir computing is you send your signals into this complicated non-linear dynamical system, which is your reservoir, and then you just take linear combinations of the signals that you get out of it to do something useful. So to illustrate this a little bit better with a very simple hardware example, not photonics, but hydronics or whatever you want to call it, where the reservoir, where our non-linear dynamical system is just simply a bucket of water. So what you do is you throw in certain objects in this bucket of water, either pebbles or grids, and then you can easily understand that depending on what you throw into your bucket, that you will set up very different dynamical patterns in the surface of this water. Now, reservoir computing works by observing these dynamical patterns and then doing a very simple linear regression on this. Now, to couple this back to what Yoni mentioned in her first talk, this is very much related to the problem of overfitting. Because if you have a complicated data set with a complicated boundary, as I illustrate here, this is something that can be very prone to overfitting. Now, obviously, if you have data which is not linearly separable, which has such a complicated boundary between different classes, yeah, then sometimes you need a complicated model. But again, you run the risk of overfitting. But this is why reservoir computing can be very useful, because what is actually going on there is that you come in with your data, you send it through this complicated non-linear dynamical system, and then you take that data from a lower dimensional space and you actually transform that into a higher dimensional space. And then you can easily understand, because there's so much more space in higher dimensions, that's okay, the different clusters will still stick together, but now all of a sudden it will be possible to separate them with a very simple linear criterion with this hyperplane here. And that means that it's a system which is very robust against overfitting. And it's also a system which is ideally suited for a hardware implementation, because remember, the only thing you need is a complicated non-linear dynamical system. And then on top of that, you add some very simple linear regression. And this is why it's very interesting to also implement this in photonics. And that's what we've been doing in collaboration with Yoni for the last couple of years in this platform called Silicon Photonics. Now, for those of you that do not know what Silicon Photonics is, it's basically us stealing the technology that was developed for silicon electronics and then using it to build chips where the information is actually carried not by electrons, but by light. And in doing so, we can shrink down the whole complicated optical setup into a very small optical chip. So here in the top right, you see the chip, one of the first chips that we fabricated that actually implemented this technology. And so the nice thing is that silicon photonics is a very mature technology. Also, not going to go into details here, but as an optical chip goes, this is a very simple technology. It doesn't require any complicated technology developments. And in essence, what you do here is build your non-linear dynamical system. You build a way for different light paths to non-linearly mix with each other. Now, the nice thing about this chip is this thing I'm not sure if you see my mouse here, are these sort of so-called spiral-like structures in between. You might think they perform a very interesting function, but actually the only role of these guys is to slow down the dynamics of the light such that the whole chip becomes slow enough that we can actually measure it. Because the funny thing about this technology is that you actually need to work very hard to slow it down so that you could measure it, whereas typically you need to work very hard to speed up your technology. So if we were just to get rid of these delay lines between these nodes in our neural network, this whole chip could run at, I don't know, hundreds of gigabit per second. So the nice thing about this technology, it's something which can run very fast, much faster than you can possibly do in traditional electronics. So let me skip here the introduction. So I hope this gives you more or less an idea what reservoir computing is and why it's useful to implement this in photonics. And now I would like to discuss some examples of how we used this technology to tackle problems where this technology could make a difference. And then we're typically looking at problems where the input is already in the optical domain, because then you do not need to translate it back and forth between electronics and photonics. So I think that makes a lot of sense. If you have an optical problem, that we try to solve this in an optical way so that we have all the benefits of speed and power consumption. And also problems where speed is indeed crucially important and where we can have a benefit compared to traditional electronics.